Ladies and gentlemen, thank you all for coming. I will now open this meeting. This is the third meeting of the 133rd session of the British Astronomical Association. We are here in the Institute of Physics in London, and we should have some viewers on the YouTube stream as well. If people on the YouTube stream want to ask any questions, if you type them in the chat, hopefully one of us, either myself or Andrew, will see the questions and relay them. And of course, anybody in the hall here can ask questions at any time. Just put your hand up. I'd like to first ask if there's any new members here who I can formally welcome to the association. Anybody, any new members or anybody who's never been to a BAA meeting before? I have already spoken to Dee and Louise, who are over here.
They're just going to isolate them and identify whether they stand up or not.
I'm going to, no. Yes, and yeah, they're actually members of the SPA, but we are welcoming SPA members to our meetings, and BAA members are also welcome to go to SPA meetings. So nice to see you, and I hope you enjoy it, and do ask if there's anything you want to know. The next thing I need to do is ask the papers secretary, Nick James, to tell you what papers...
Slightly out of date.
Not Nick James, sorry. Paper secretary, well, you do so many things, I just... this is default,
7 years ago?
Default name.
7 or 8 years, yeah.
No, Nick James used to be the paper secretary, actually. But for the past 7 years, it's been Jeremy Shears, and he is now going to tell you what papers Council today approved for publication in the journal.
Will do. Perhaps I just ought to speak really loudly, and then you think I'm Nick James. Four papers were accepted by Council for publication. The first is Harry Thornton, Leslie Ray and the Rise and Fall of the Moon by Martin Moberly. The 2022 Western Elongation of the Planet Venus by Paul Abel. And we have The Opposition of Jupiter, 1955 to 56 by Richard McKim. And the fourth one is Noctilucent Cloud over Britain and Western Europe, 2022 by Ken Kennedy. Thank you.
The reason why we have a paper about Jupiter as it was in the 1950s, which may seem a bit out of date, is because it wasn't covered at the time in the journal, apparently. And Richard McKim has been very assiduous in going through all the records and noting where there are gaps in the reports, and has been actually going through the original observations from that time to fill that gap and to analyse them for that year. So that's a very worthy enterprise. So that's why that is being published now, or shortly. I will now tell you about what events to look forward to. We are continuing with our series of webinars, and we've got a webinar on the 18th of February, which is a Saturday, and that is the solar section meeting for this year, will be held on Zoom, and anybody within or outside the BAA can join in that. And that is on the 18th of February at 2 o'clock, and it lasts all afternoon. And to find out how to join that, you look at the website at the meeting section or the forthcoming events section on the website. And the next webinar after that will be about Jupiter, multispectral imaging of Jupiter, and that's on Tuesday, or is it Wednesday? 1st of March. It's on the 1st of March at 1900 on Zoom. And then the next actual physical meeting, we're having a meeting in York. We're having a joint meeting with the SPA. It's called the Back to Basics workshop, where we have talks about basic amateur astronomy and beginner steps in becoming an amateur astronomer. So that is the 11th of March in York, although that's the same day as the Practical Astronomy show in Kettering. So you've got a choice of what event to attend on Saturday, the 11th of March. Then we have another section meeting, but this time a real section meeting, actual meeting in Bedford on the 19th of March for the Deep Sky section. And their meeting's always great fun. So if you want to book up, you need to book up for that on our website, and you'll find a link to put your name down for the Deep Sky section meeting, which occurs all day on Saturday, the 19th of March. Sunday, the 19th of March. Apologies, Sunday. Yes, I remember that. It's a Bedford school, and meetings there are always on Sundays, and they do very nice meals. A very high class of school meal there.
We're not at school.
Well, you can go back to you can pretend you're in your youth again. It's a bit of a stretch for many of us. Most of us. Then the next time we are here in the Institute of Physics will be on the 29th of March in the evening. That's a Wednesday evening. That will be 5:30 in the evening. We have a special general meeting then, and that is a thing that we have annually to discuss whether to raise the subscriptions in the next year. And that's a thing that all the members have input in. So this is your notification that there will be a special general meeting on the 29th of March here at the Institute of Physics to purely for the purpose of discussing the subscription level for the next session. And then after that, we will have some interesting talks that I can't remember what they are. And also, the Winchester weekend is coming up. That is 14th to 16th of April. Booking is now open. There's a few places still left. It's our main residential event. You can go and stay. You don't have to go and stay. You can go there just for the day if you like. But most of the people stay in the accommodation, which is at Sparsholt College, which is in the countryside. It's not exactly in Winchester, but it's about a few miles outside Winchester. And we can actually do some observing there. It's reasonably dark there. And we have the Friday evening lecture and then a full day of talks on the Saturday and some more events on Sunday. And on the Saturday includes a section meeting of the Mercury and Venus section. So that's the Winchester weekend. You have to book up for that, and the price of that is being held the same as last year. It's still very good value, I think. There's a non-BAA event coming up, which I will mention, the Astrofest, which is back after a few years' gap due to COVID. The Astrofest, London Astrofest, or the European Astrofest, as it styles itself, that is the 3rd to the 4th of February, Kensington Town Hall, and the BAA will have a stand there, and we'll be selling our publications and trying to recruit people. I have another announcement, which is not a BAA thing, but I've been asked by Hampstead Scientific Society if I can help to find people who could help to run their observatory, which is in Hampstead, and they open it to the public on Friday and Saturday evenings, traditionally in the winter months, but they've no longer got enough volunteers to do that. And so anybody who knows how to operate a telescope, and if you live within reach of there, they'd very much like to hear from you, and you could, if you contact me, then I could get you in contact with them. Their observatory houses a 6-inch Cook refractor from about 1860. It's a very historic instrument, still works very well, and it's used mainly for looking at the planets. It's in the middle of London, but they can still see quite a bit. So that's the Hampstead Observatory. So a little bit earlier than advertised, we can now move on to our first of our professional speakers. We've got 2 professional astronomers speaking to us today, one about the deep space and one about planets. And the first is Professor Andy Bunker. Andy is an expert on galaxies. He did his postgraduate, and indeed his undergraduate and postgraduate training at the University of Oxford. After that, he worked at various other universities, and he went to Australia for a while to be head of astronomy at the Anglo-Australian Observatory, which has actually changed its name now. It's now called the Australian Astronomical Observatory, still AAO, since the UK stopped funding it. Although the telescope there is still called the Anglo-Australian Telescope. Anyway, Andy Bunker is now a reader in astrophysics in the physics department in Oxford, and he is on the instrument team for the NIRSpec spectrograph on the James Webb Space Telescope. I don't wish to embarrass him too much, but his biography on the St. Catherine's College website is a bit out of date. It says there that it is expected that the James Webb Space Telescope will be launched around 2018. we know how that worked out. And he also does work helping to edit the memoirs of the monthly notices of the Royal Astronomical Society, which is a major publication on astronomy in professional research in the UK. So Andy Bunker is now here to talk to you about finding, or how he hopes to be finding, the most distant galaxies with the James Webb Space Telescope. Thank you.
Well, thanks very much for that very kind introduction. I shall be editing my webpage later. And it's really a pleasure to be here. I was actually a member of the BAA in the 1980s when I was a teenager, and a very keen amateur astronomy, and that very much led me on to a path doing physics at university and ultimately ending up as Professor of Astrophysics at Oxford. So I think, the sort of wonder of the universe that captured me as a teenager has sustained some of my research in the many decades since. So I'll be talking about finding the most distant galaxies using our latest new toy, the James Webb Space Telescope. And I'd like to acknowledge some of my team at University of Oxford who are working with me on this endeavour, who we have a rogues gallery and a little potted history of what each of them are working on. Iman Wallace on the right there is my graduate student. The other four, Jacopo, Alex, Gareth and Ayush, are postdocs working with me, analysing data from the James Webb Space Telescope that's come just in the last few months. And in fact, we had some observations taken last week. We have more coming in the next few days as well. So as you're aware, we had a very nice Christmas present just over a year ago in Christmas 2021. After a long, long wait, an Ariane 5 rocket launched the James Webb Space Telescope. Now, I joined the project, the instrument science team for one of the instruments in 2004. So I had an 18-year wait. When I joined in 2004, we were told launch would be in about 5 years, and that was quite a long 5 years, some sort of relativistic effect. But after many years and after about $10 billion US, this is the most capable telescope ever launched into space. And it was very exciting to witness that. I was supposed to go out to French Guiana to see the launch, but because of COVID, that got cancelled. I ended up watching it from my parents' house in Chichester, but not quite the ambience, but still pretty impressive. And this was our last view of James Webb after it had separated from the nose fairing of the Ariane 5, and they put a camera quite late on in the process in the final stage of the Ariane 5, so it had jettisoned the fairing, and this thing wrapped in tin foil. This is James Webb, and then this, after it had separated, after a few seconds, the solar panel popped out to start getting power. Or at least I thought this was the last image of the James Webb Space Telescope, but then I talked to my colleague Peter Jacobsen, who from his back garden in Copenhagen had imaged James Webb as it a few days after launch, and it's this dot tracking across the sky. And this isn't actually due to the motion of James Webb itself that was moving linearly away from the Earth. It's actually the parallax due to the rotation of the Earth and Copenhagen moving over a period of hours to provide the parallax. So that's quite cute. By then, 10 days after launch, it was about 16th magnitude, but he had a nice setup in his back garden. And Peter was the former principal investigator of the instrument I'm involved with up until his retirement from the European Space Agency, but he's still very actively involved on the team. So you've probably all seen pictures of James Webb. Here's an artist's rendering. So it's huge. It's 6.5 meters in diameter. That's actually bigger than the nose cone of the rocket it launched in. And in order to achieve that, it folds up. So it has 18 hexagons, and it folds up into 3 sections, so it can slot within the nose cone of the rocket. Also, you notice, unlike the Hubble Space Telescope, it doesn't have a tube. It has 5 layers of mylar, which deploy, and the idea is that the sun is on one side all the time, and then the optics are constantly kept in shade. This makes it a lot cheaper, a lot lighter, and able to launch a much larger telescope. So Hubble's 2.5 meters, this is 6.5 meters in diameter. And unlike Hubble, it's not in Earth orbit. So Hubble orbits about 600 kilometers up. That was just within range of the space shuttle when that was functioning, so that they could go up, they could repair it, which, boy, they needed that initially, but also they were able to update the instruments. I was heavily involved with many of the instruments over the years on Hubble, such as the near-infrared camera NICMOS, and more recent instruments as well. And that's great that they could constantly upgrade it. Unfortunately, of course, Hubble drags on the atmosphere. Eventually, that will come down, so it's a finite lifetime mission, but they've done well to boost it repeatedly, so it's been going over 30 years. But unfortunately, of course, if you're in low Earth orbit, it orbits every 90 minutes, so you're constantly switching from sunlight to shade. The telescope is heating up, cooling down, that produces jitter, and also you can only observe on the dark side of the Earth. James Webb is out at a point called L2. That's the second Lagrange point in the Earth-Sun system. Don't worry about the jargon. This just means it's kind of a stable point where approximately the gravity of the Earth and the Sun balance, and you don't need to employ a lot of propellant station keeping. And it also has the great attribute that the Sun, the Earth, and the Moon, the 3 brightest objects, are always on one side of the spacecraft. So you can imagine they will always be down here, and the optics will always be shielded from them. Disadvantage, if anything goes wrong, very difficult to go out and fix. There is a grab handle on the back, so maybe in 20 years' time, perhaps China or whoever is doing space exploration there, we're able to go and fix it, but we can't go out there now. Unfortunately, everything did work. There was a month of terror really after launch where the mechanisms deployed, the main mirror folded out, the secondary deployed, and then like the sails of a yacht, these 5 layers stretched out. And there were a lot of potential single-point failures. They took it very slowly. Everything worked perfectly. And after launch, there was 5 months of commissioning, making sure the instruments worked properly, also allowing the telescope to cool down. It's passively cooled, and it's cooled to 50 degrees Kelvin, so that's about minus 220 Celsius. Don't know what that is in Fahrenheit, but it's pretty cold. And there's one instrument, the mid-infrared instrument called MIRI, which has a closed-cycle cooler or refrigerator that gets even colder than that. Works in the mid-infrared, needs to be, which is the thermal, needs to be exquisitely cold in order to be sensitive. So the size of the sun shield's about the size of a tennis court, so a big piece of kit. And after the commissioning, after 6 months after launch, the first images were released by Joe Biden. You can see him gazing longingly at this very deep image. And what we see here, this is a foreground cluster of galaxies. These are the yellow and orange blobs. And behind, it's gravitationally lensing the light of even more distant objects. So that's Einstein's general relativity, mass bends light. It's acting as a magnifying glass, allowing us to see the even further universe. And I'll show you a few results from those early observations, but I'll talk a little bit now about the instrumentation. So there are 4 instruments. I already mentioned mid-infrared. That works between 5 microns and about 30 microns. So that's similar in wavelength to the thermal infrared cameras that firemen use to find bodies in buildings. So that's what we regard as heat radiation. I'm involved with NIRSPEC. I'll say more about this later on. But this works between about 1 micron, so that's about just beyond what you can see with your eye, all the way up to 5 microns. And there's a couple of other instruments, an imager, NIRCam. NIRCam is headquartered in the University of Arizona in the US, and a NIRIS, which is the Canadian contribution. That's both an imager and it's able to spread the light out like a rainbow as a spectrograph for every object over a field of view. So that's quite powerful. I'll come back to spectroscopy later on because that's the work I'm principally doing. So 4 instruments, 1 provided by Canada, 1.5 provided by Europe, including NIRSPEC, that's provided by European Space Agency, built by Astrium, and we also provide half of the MIRI instrument. The other half comes from the US. And here's some of my colleagues involved with the NIRSPEC instrument. We have a full-scale mock-up of the instrument here. So this would be housed in an enclosure. You have some filters. You have a grating or a prism here, and it will separate out the light, and it will go to 2 quite big infrared detectors, each about 2K by 2K in size. These are some of my colleagues who I've been working with since 2004 on building and commissioning the instrument. And now the team is greatly expanded. We all now have postdocs and students working on the data that's finally come in. So NIRSPEC is a spectrograph, so it spreads out light with wavelength. So we want to take a spectrum of objects, and that tells us a lot about the object. So I'll come onto this later on, but we're interested in emission and absorption lines. These are like the fingerprint of elements, and we can study both the composition of galaxies, but also the temperatures of stars. We can study if dust attenuates light. We can study the rate at which stars are born. And it's got a number of different modes. So we have some fixed slits. We would use those for spectroscopy of planet transits, for example, seeing a planet passing in front of a star, and to do spectroscopy of that. We have something called an integral field unit. So that's essentially taking a 3-dimensional image, if you like. So we're able to get a spectrum at each point over a field of view, a very small field of view, 3 by 3 arc seconds. So that's a tenth the diameter of the full moon. Sorry, it's very, very much less than that. Sorry, my unit scrambled up, but tiny patch of sky. But you're able to take a spectrum at each point over that. And the spectrum gives you the 3rd dimension. It tells you the wavelength. So it's great for dissecting galaxies, also seeing rotation of galaxies. So we can measure the masses by measuring the spectrum and finding the velocities of different components. That's what we call the rotation curve. And a more massive galaxy will have its stars orbiting at higher velocity. So we can essentially weigh galaxies close to the dawn of time. But the mode I'm going to focus on in this talk is the multi-object spectrograph. So we're able to take spectra of many objects simultaneously. With Hubble, we can only do one at a time, really. Ground-based, we can do multi-object, but we can't have great sensitivity from the ground beyond 2 microns because the atmosphere is hot, and also the atmosphere doesn't transmit for a lot of those wavelengths. So for the first time with James Webb, we can go to long wavelengths, and we can hit many galaxies at once. And the technology behind this is called a micro-shutter array. So we have lots of, this is an electron microscope image with lots of little windows that we can command to open or close. Now, one of the rules of space exploration is have as few moving parts as possible. This array has 250,000 shutters, windows that open and close. Now, the failure of any one of those is not critical, but it is very, very ambitious. And you could command them to open individually. And what you could do is you could have your favorite space agency logo imprinted, or perhaps more usefully, open them on particular galaxies in the distant universe. So the reason why you want to have a shutter or a slit is there is sky background. You might think there's no sky background from space, but in fact there is background light. It's the dipole light from our own solar system. There's scattered light within the telescope. So by having a slit to cut down the background light, you're just letting in the light from that distant galaxy. You're not adding to the noise by having extra light. So if you think about, we don't observe stars in daylight because the background is too high. We can do it at night. It's the same argument that the low background environment gets you less noise and you're able to see fainter objects. So this is why we want individual shutters to be able to open, so that we're only letting light through in a particular row or on a distant galaxy. So this is what we have. You know, we can configure it to do typically about 100 galaxies at one shot, each of which will achieve a little spectrum spreading from the blue end, that will be about 1 micron, so not blue light at all the way to about 5 microns or so. So we're able to get spectra of distant galaxies. So I just might try and motivate why we want to see distant galaxies. So the universe itself is a time machine. Light travels at a very fast but finite rate. When we see the sun, we see it as it was 8 minutes ago. We look at the nearest star, we see it as it was 4 years ago. Nearest galaxy, Andromeda, about 1 million years ago or so. I'm interested in finding galaxies that light has been traveling more than 10 billion years. So that's most of the lifetime of the universe, twice the age of the Earth. So when the photons left, it's not only the dinosaurs didn't exist, the Earth didn't exist either. So the reason why we want to do that is we can look then back in time. We can see what galaxies were like when the universe was in its infancy. And we can compare with galaxies today. That's where the astrophysics comes in. Conditions were very different. We want to see how galaxies assemble the first generation of stars, how they assemble their mass, perhaps through merging. What galaxies were like when the chemistry of the universe was very different. It was principally hydrogen and helium. The heavier elements had yet to form. So it's a real physics problem, and you might think you can just model it on a computer, but it's too complicated for that. We actually need to do the observations to understand. So here you are, represented by the Hubble Space Telescope. As we look back through space, we look back in time. So we're interested in studying things like the Hubble Deep Field that was taken by the Hubble Space Telescope back in 1996, and I worked on this quite a lot, and that pushed back in time. And then more recently, the Hubble Ultra Deep Field that I led the first paper, research paper on. This still is the most sensitive image of the night sky ever taken. That got us even further back in time. Not quite to the era of the first galaxies, but certainly into the first billion years of history also. So how can we measure distances to galaxies? So I've shown the motivation of finding distant galaxies, but we can't get a tape measure out. How can I convince you these things really are distant? So we're helped a bit by physics. So there's a famous Doppler effect. If you stand at a street corner as an ambulance passes, you notice the pitch drops as the ambulance recedes. And this is due to the wavelength of the sound being squashed as it approaches and being stretched out as it recedes. There's a similar, not identical, phenomenon with light due to relativity. So an object which is approaching, the photons, their wavelength will be shortened. That means blue shifted. And an object which is receding, the photons will be stretched out, and that will be red shifted. And if we're able to measure this stretching of the photons, that gives us the expansion factor of the universe directly. So if I expect an emission line to appear in the optical, but I see it at twice the wavelength, it means the universe is stretched by a factor of 2 since the photons left that distant galaxy. And with a bit of general relativity, you can translate that to a distance and a look back time. And here, this is stolen from my former graduate student, Elizabeth Stanway, who's now a professor at the University of Warwick. This in human years down the bottom, going from the 1960s to 2010 or so when she wrote her thesis. This is on the y-axis. This is the redshift or the expansion factor that we have reached as a function of time. So as time progresses, we're able, thanks to technology improving, to see further and further back in time. So when I started in the mid-90s, we could see about 2 billion years after the Big Bang, and these were a few very luminous objects called quasars and radio galaxies. But in more recent years, we've pushed even further back in time, and even fainter objects. We're now seeing normal galaxies, not those which are super luminous thanks to a central engine like a black hole. We're seeing more normal galaxies all the way back to within 10% of the Big Bang. So we're looking 90% of the way back through time to the early generations of stars. So how do you go about finding these distant galaxies? And then I'll talk about how do you prove it really is distant. So just one physics plot. Apologies, I know people generally aren't physicists, but there were two big developments in the 20th century in physics. One was relativity, and that underpins what we think is the expansion of the universe. And the other thing was called quantum physics, and that is that you have atoms, and an atom essentially is a nucleus with some electrons orbiting around it. The electrons are negatively charged, they have very low mass, and they can hop between orbits. But the miracle of quantum mechanics means that there are only certain allowed energy states. So when it drops from an excited state to the ground state, it emits a photon corresponding to that energy difference. And different atoms have different fingerprints, if you like, different allowed energy levels. So we're able to see from the emission lines that are released when an electron de-excites between two energy levels, we know what the atom is that oxygen, is that hydrogen, whatever, and we're able then to get the chemical composition of galaxies. But also, these transitions have a very particular wavelength or frequency. But as the universe expands, as I said, those photons will be stretched in wavelength. So we will see the same fingerprint, but the photon wavelengths will be scaled by a factor, and that factor is 1 plus the redshift. So if we can see the fingerprint of a particular atom in the spectrum of a distant galaxy and measure the wavelength, we have the redshift. And we help further to locate distant galaxies because galaxies aren't the only thing in the universe. There's a lot of gas between the galaxies called the intergalactic medium. You can imagine a galaxy, the far side of the universe, the light is coming towards me. It's not passing through a vacuum. It passes through lots of clouds of principally neutral hydrogen along the line of sight. Each of those will absorb a bit of the light, and it will absorb at the same frequencies that will cause an electron to hop up to one of these other energy levels. So this has the effect of producing these little notches in the spectrum, these little dips. This looks like a kind of a picket fence. Each of these, this is some distant galaxy. It's a cartoon, not a real spectrum, but the spectra really do look like this. These little notches here correspond to the light passing through a cloud of neutral hydrogen, and it excites a transition from the ground state. So what happens is these clouds of neutral hydrogen, they eat away at the flux. So above the wavelength at which these transitions start, so these are low energy photons on the left, higher energy on the right, no absorption occurs. But then here, we have these absorption by neutral hydrogens. This eats away the flux. So you can imagine, if I have a filter that just lets through red light, I get lots of flux. If I have a filter that just lets through green light, that's eaten away some of it. And then if I have a filter now in the ultraviolet, essentially no flux gets through because the neutral hydrogen absorbed all that light. So this is great because you can imagine a lower redshift galaxy, that means a more nearby galaxy, that yellow region would simply shift all the way to the left, and I would see that galaxy in all those filters. So if I have a galaxy which vanishes at blue wavelengths, it's likely to be extremely distant because the universe, the gas between the galaxies has absorbed that flux. So, how to find distant galaxies? So here we have, until very recently, the deepest image of the universe ever taken, the Hubble Ultra-Deep Field, and it's about the 10th of the size of the full moon. It's about 3 arc minutes across, and you can see if you go down to the noise level, there's about 10,000 galaxies there. Which one's the most distant? So I could go and take a spectrum of each and every one, 10,000, be a very generous telescope time assignment committee to give me time to do that. They're not going to do that. So you need a way to find a short list of likely suspects to be very high redshift. So we can pick out the red blobs because they are either intrinsically red galaxies or red because they're highly redshifted and the universe, the gas between the galaxies, has absorbed the light. In fact, me and my team, we were the first to analyse this. We identified many red blobs, about 50 or so, which were consistent with being extremely distant galaxies. But you're probably sitting there a little bit unimpressed. It's just counting red dots in Hubble images. You know, where's the proof that these really are distant? So to prove it, you need spectroscopy. So spectroscopy is key. We can select candidate distant galaxies by colours in images through different filters, but we really need to confirm that. So a red dot could be a high redshift galaxy. It could also be an intrinsically red galaxy, either because its stars are old, or it has a lot of dust. And dust is formed naturally in the universe in star evolution, stellar evolution in supernovae. Dust has the effect of reddening light. Blue light is scattered far more than red light. That's why sunsets are red. So it could be that, or embarrassingly, it could be a very low mass star within our own galaxy. So we really need to tell the difference, otherwise, it's not science. So it's not really been possible. We had heroic efforts using the Keck telescope in Hawaii in the 2000s to get a few spectra. We confirmed a handful, but most were impossible. They were either too faint or they didn't have line emission in the region that we were looking to confirm. So we have to go to longer wavelengths and a more sensitive telescope. So we really want to probe back. So we are here today, and as we go up the plot, we go further back in time. These are some of the galaxies in the Hubble Deep Field and the Hubble Ultra Deep Field. We want to push within the first billion years of history, and that's very interesting because that will host the first generations of stars, and also the gas between the galaxies undergoes a phase transition. So before about a billion years after the Big Bang, it was mostly neutral gas between the galaxies. And around a redshift of 6, that's about a billion years after the Big Bang, suddenly that gas is fried, it's ionized, turned into a plasma. And one of the puzzles is what causes that. You need a big reservoir of highly energetic ionizing photons to achieve that. Where do they come from? So it's thought perhaps, active galactic nuclei, that's supermassive black holes, quasars, might contribute. There simply aren't enough of them. Could be young star-forming galaxies. We know when stars are formed, you form, it's not like a car production line, you don't make all stars the same. You form a spread of masses called an initial mass function. There are more low-mass stars than high-mass stars, but the very massive stars can shine very bright, very hot, and therefore very blue, and can produce ionizing photons. And if there's enough star formation early in the universe, that would be the solution to ionize the gas between the galaxies. But this is still an unsolved problem. So we can, with James Webb, we can do better from the ground and from Hubble. We can get more sensitive. We can also observe at longer wavelengths, and that's crucial for things which are at high redshift, that is very distant, because the light is stretched out. It's stretched out to such an extent that the visible light just isn't there anymore. That's the region I showed you that had been eaten away by the gas between the galaxies. We have to go to longer wavelengths. We have to go beyond 2 microns or so. And we also would ideally want to hit many objects at once. So James Webb delivers that. It's a very cold telescope with a big mirror. It has exquisite resolution, thanks to it achieving the diffraction limit. And it has a multi-object capability. So we can start to understand the earliest galaxies. So this just gives you the wavelength coverage going from 1 micron, that's about 50% longer wavelength than you can see with the human eye, all the way up to 5 microns, a lot longer wavelength. We have 2 different modes. We have a prism where we get all that wavelength coverage at once, lots of little rainbows in our focal plane, or we can put in gratings, and that spreads out the light more aggressively with wavelength. Therefore, you get better wavelength resolution. We're able to see lines from elements such as hydrogen, also nitrogen and oxygen and carbon, and we can see these out to extremely high redshift, all the way out to redshifts beyond 10. So this is unprecedented. And I've, as a reward for being involved in the team that built the instrument, we get some guaranteed time, or GTO observations. So we get about 900 hours for our team of James Webb Space Telescope time. And we've joined forces with our colleagues on the NIR-CAM team, the imaging, to form a project called JADES. What we want to do, and in fact we are doing now, is confirming the most distant candidate galaxies. We can also measure the rate at which gas is being converted into stars. And we can do that from those emission lines. So the most massive stars, as I mentioned, they shine very bright, very hot. They're short-lived, about 10 million years, and they produce ionizing photons. These are the O and B stars that you can see even in our galaxy in star-forming regions. So the fact they produce ionizing photons, if there's gas, hydrogen gas around them, it will ionize that, And when the electrons get recaptured, we see those emission lines. We can see the recombination lines of hydrogen. And just by counting those photons, we know how many of these massive stars there are. Because the massive stars are short-lived, that tells us the rate at which stars are being born. And we can reach star formation rates equivalent to 1 solar mass per year, 1 times the mass of the sun per year, all the way out to redshifts beyond 6, so within the first billion years of history. Just for reference, our own Milky Way is forming stars at about 3 times that level. So we can see things which are less actively forming stars than the Milky Way all the way across the universe. So that's not bad. We can also see how old the stars are. And by measuring the velocities within a galaxy, like the rotation, we can get something called the kinematics. That tells you the rate at which the stars are orbiting the centers of the galaxies, and that gives you the mass of the galaxies. We can also search for elements which are heavier than hydrogen and helium. Hydrogen and helium are formed in the Big Bang in the first 3 minutes. After that, not a lot happens until the first stars form some hundreds of millions of years later. And then the stars are incredible nuclear furnaces. They fuse ultimately to elements such as carbon and even all the way to iron, and heavy elements, even heavier elements, are produced in the last split second of the lives of stars. So all the heavy elements that form a lot of us, all the carbon, all the oxygen, all the iron and hemoglobin that makes your blood red, all that iron was formed in the cause of collapsing stars, supernovae, right? So it's quite sobering. So if we're able to look for the fingerprints of these heavier elements, we can get the chemical history of the universe. So we know earlier in time, fewer of these elements should have formed because there's fewer generations of stars go before. And the holy grail, if you like, is to find the first generations of stars to form where you just have hydrogen and helium and nothing else. Still looking for that? James Webb might discover that. That will be a major discovery, the first star formation in the universe. And we're also interested in what happens in the middle of galaxies, and we believe that each galaxy hosts a supermassive black hole. We can also study that with JWST. So I promised you a little bit of the early science, so let me address that now. So a little hard to see, but this is that image that Joe Biden was gazing at earlier in the talk. This is the first image publicly released from the James Webb Space Telescope, as I mentioned. This is a cluster of galaxies, and these little streaks, you can see, these are much more distant galaxies whose light has been magnified and distorted by this massive foreground cluster. So that has the advantage of boosting the flux. It's a magnifying glass. Here we have, I'll show you a zoom in of this. Here we have these different emission lines I already mentioned, those lines of hydrogen. We also have a couple of lines of oxygen here. This is an extremely distant galaxy, and for the first time we're seeing a spectrum at around 4 microns. And we're able to say that there's oxygen there, so we can measure the abundance of this heavier element. We can also get the temperature of the gas between the stars, and that's because we have a couple of different lines of oxygen in different excited states. So that gives us the temperature of the interstellar medium, we call it, and we can compare that with interstellar medium of the Milky Way and galaxies today. And it's a lot hotter earlier in the history of the universe. We don't really know why. It's possible that the stars that are forming are subtly different, that you favour higher mass stars, that favours a more blue spectrum. That might be expected in low metallicity environments, but it's still something of a puzzle. So we're challenging now the people who simulate star formation in the early universe to explain why the interstellar medium should be so much hotter. And as I mentioned, one of the techniques is to image in different filters and to find objects which disappear at short wavelengths like this and are present at long wavelengths. These are candidates of being even more distant galaxies. And here we have a candidate found by another team, not my team, where you can see it's present at 2 microns all the way up to 4 microns, and it completely vanishes at shorter wavelengths. And this could be this break. Below this break, that's the effect of the neutral hydrogen in the universe absorbing all the flux, and then it picks up. And it's argued that this might be an extremely distant galaxy. But I caution this one doesn't have a confirming spectrum. But my team, the JADES team, that's the collaboration between NIRSpec, my instrument, and NIRCam, the imager. Just before Christmas, we released a couple of papers which spectroscopically confirmed the most distant galaxies yet known. So if you squint a bit, this is in the background. This is something called the Goods field. This is around the Hubble Ultra Deep Field. It's a patch of sky in the south, in the Fornax constellation. Very, very well studied. We have imaged this with James Webb. It was previously imaged with Hubble, and we identified red blobs. And then we turned to the spectrograph NIRSpec, opened those shutters that I showed you on some of these red blobs, and 4 of them turned out to be extremely high redshift. I'm going to show you a spectrum. So this looks a little bit noisy, maybe a bit hard to love, but I'll describe what's going on. You see that spectral break goes to essentially zero flux. So we've shown that there's a strong spectral break. It's impossible to mimic this feature from low redshift galaxies or from low mass, very red stars in our own galaxies. So we've shown for the first time that out to a record-breaking redshift 13, these are the most distant galaxies yet confirmed. We have candidates to be even more distant. So light has been traveling for 95% of the way of the age of the universe to reach us. And the brightness of these galaxies are equivalent to a candle at the distance of the moon. They're about 30th magnitude. So it just gives you a feel for how impressive this piece of kit is. And those ones, those spectra I showed, you had a continuum break and some continuum, but we also have emission lines all the way out now to redshift 9. And you see we're able to see oxygen lines all the way out to extremely high redshift. So we haven't yet found the first generation of stars, but we're still looking. But this tells us about the chemical enrichment history of the universe, which is very interesting. So this plot was produced by my postdoc Alex Cameron, and these 2 lines are lines of oxygen. Here we have a line of hydrogen and another line of oxygen. And in fact, the ratio of these lines tells you the temperature of the interstellar medium, the gas between the stars. And using that ratio with other lines as well tells us the abundance of these heavy elements. So we're able to see, and in fact, there's less oxygen in this galaxy than there would be in the Milky Way. That's no surprise because our own Milky Way has had many previous generations of stars. So we're seeing not the first generation of stars, but maybe the second or the third generation of stars here. So in a very, very young, energetic galaxy. We're also able to measure the age of these galaxies. So a galaxy, you see, is composed of its component stars, and you add up all the starlight. These emission lines, these spikes, that principally comes from the gas between the galaxies, but this continuum, that's essentially starlight. And you're able to look for very age-sensitive features. So one of these here is this dip. You see this dip, this spectral break? That's called the Balmer break. And that's very strong in stars which are A-type. So Vega in our own night sky is an A-type star, and that has quite strong hydrogen absorption, which produces this little discontinuity. And A-type stars, they're a few times the mass of our sun, 2 or 3 solar masses. And if we see that spectral discontinuity, we know that the underlying age of the stellar population is somewhat old, because all the massive, very blue stars probably have died some time ago. Otherwise, they would be dominating the flux, and they don't exhibit that spectral break. So we're actually able to get the age of that galaxy, and it's 100 million years or so. Probably unimpressive. The age of the sun is 5 billion years. The age of the Milky Way is perhaps 10 billion years, something like that. But I'd remind you that this is seen within the first billion years of history. This has pushed the formation epoch back even further in time. So although these aren't particularly old ages, the fact they're old ages seen when the universe was young is significant. So we're pushing our understanding of when galaxies formed. So if I can go on just to what we've learned so far. So with the James Webb, and specifically with the NIRSpec instrument, we're able for the first time to do spectroscopy at wavelengths beyond 2 microns. This is absolutely critical to confirming the most distant galaxies in the universe. And we've been able to achieve this by spreading the light out. Not only that, we've hit many hundred at once. And I've shown you the paper that came out just before Christmas, where we confirmed the 4 most distant objects yet discovered. So that's fun. Not only that, we're able to get the mass, the stellar mass and ages of these distant galaxies. So that tells us, in a way, the formation history. We think our own Milky Way has been assembled over billions of years through mergers of distant galaxies. In fact, we're likely to merge with the Andromeda galaxy in the next 5 billion years, but the sun will have burnt out by then, so I wouldn't worry too much. And we're seeing at high redshift early in the history of the universe these low mass subunits forming. So the masses we measure are far less than the Milky Way, and we think the Milky Way to assemble over time through mergers of these distant galaxies. We're able to measure the star formation rate, the rate at which the gas is being converted into stars. And as I already mentioned, we can see not only lines of hydrogen, but also lines of oxygen and carbon. And then, therefore, we can get the chemistry, the chemical composition of these distant galaxies. And that's interesting because we expect the enrichment, the chemical enrichment, to change with history. That early on it was just hydrogen and helium. Later on, we form the heavier elements. We're able to measure those metallicities. Astronomers or astrophysicists is very cavalier with the word metal. We have hydrogen and helium. Anything heavier than that is a metal. Yeah, I know, but we're able to measure that. The search still goes on for the first generation of stars to form. I think there's a 50-50 chance with James Webb that we will see that, maybe in the next few years, so watch this space. We can also quantify the amount of dust produced. So, as I mentioned, dust is formed naturally within stars, and that has the effect of reddening starlight. And in fact, in some cases, it completely obscure at optical wavelengths galaxies. We're able to actually measure the amount of that dust thanks to James Webb Space Telescope, and also other important facilities on the ground, such as ALMA in Chile. I haven't really touched on, but it's an area of active research, supermassive black holes at the center of galaxies as material spirals around that produce an accretion disk. And it's kind of ironic that black holes, very, very dark, actually power the most luminous objects in the universe, which are things like quasars, and that's a superheated material spiraling into the black hole. We have been studying these with James Webb. I'm not focused on this in my talk now. I focused on star-forming galaxies, but this is an area of important research. And one of the important questions is people have detected black holes at the centers of galaxies, which are 1 billion times more massive than our own sun. One of the key questions is how you assemble that mass of a black hole. You have to accrete matter very, very quickly or merge very efficiently, and that's still an outstanding problem of astrophysics, and James Webb should shed some light on that. We're also able, with James Webb, to get the dynamics of the galaxies, particularly using this integral field spectrograph I mentioned earlier on, where we're able, over a very tiny field of view, to get a spectrum at each point. We can see the relative Doppler shifts of the stars as they orbit the center of that distant galaxy, and that will give us the mass of that. And the mass not only will be the luminous stars, it will also be the dark matter. So we are charting how much dark matter there is in galaxies early in the history of the universe. And dark matter is believed to seed galaxy formation. That's where the dark matter overdenses, that's where the gas coalesces, and then over time, that gas through gravity will accrete, become denser and hotter, and eventually ignite the first generations of stars in these dark matter halos. So we're able to see that. And we are currently working on a big problem, which is about 1 billion years after the Big Bang. As I mentioned, the gas between the galaxies goes from being neutral to being ionized. What provided those photons? Is it star formation? Is it AGN? And if it is star formation, do we have enough escape fraction? That is, the fraction of these ionizing photons that form it on the photospheres of stars, how many battle their way out into the intergalactic medium to ionize the gas between the galaxies. That currently is unknown, but my team is constraining this. And above all, every new big telescope, not only does it tick off the wish list of existing science problems, but it always finds something unexpected in and surprising. We've had a couple of examples of that, one of which I mentioned already was the gas between the stars in distant galaxies seems to be a lot hotter than it is in the Milky Way. Why? I mean, you ask a theorist, they always have 10 different theories, but which one is the truth? So you know, I think I'm looking forward to being surprised and to open new avenues of research. So it really is an incredibly exciting time. I mean, over the last 30 years, Hubble has been delivering excellent data, and that continues to deliver. James Webb is a game changer. It's more sensitive than Hubble. It works at longer wavelengths. Hubble still has a role to play in the optical, in particular, wavelength shortward of where James Webb operates, and also crucially finding some of the targets for us to go after with spectroscopy. But James Webb is the most expensive, the most ambitious project, and it is delivering. I mean, every day on our preprint server where people post their latest research, there's 5 to 10 papers using James Webb Space Telescope. This is revolutionizing the field. And my own team, the NERSPEC team, is just one part of many groups working on such data. Although we're in the privileged position of having built the instrument, we get guaranteed data, and we still hold the record for most distant object. We still have the most sensitive spectrum ever taken. And we, as I mentioned, we have more data being taken next week. So it keeps me and my team extremely busy. But after many years waiting, it's good to see the real data. So I think it's an exciting time to be an astrophysicist. And I think NASA in particular are very good on the public outreach aspect. Some of the web press releases are spectacular and really do credit to the revolutionary nature of this telescope. So thanks very much for listening.
Thank you very much, Andy, for that up-to-the-minute talk about the James Webb Space Telescope. Any questions? Yes, Martin.
First of all, I'm very glad that we can all build our own. That's reassuring. Both questions are regarding bandwidth. In terms of dust attenuation, I mean, I've had some demonstrations seeing, you know, how shorter wavelengths can get absorbed by water, but you don't really actually know what the spectrum of the absorption is. Do we know what the spectrum of absorption of blue and whatever colour light is?
So not exactly. We know in the Milky Way there's a particular dust attenuation law, and it has some feature around 2,000 angstroms, which is supposed to be due to these buckyballs of carbon, these C60 molecules. But if we look in the small and large magellanic clouds, the neighbours to our Milky Way, the dust attenuation law seems to be different. So that's a bit of a puzzle. So perhaps the dust forms slightly differently there. And at high redshift, we don't actually know. So what we are doing, work done by collaborators of mine, is look in detail at these spectra and see whether we can understand what the dust attenuation law is. Because it might be very different, because there are different pathways to form dust. You can form it in red supergiants, you can form it in supernovae. Dust might be affected by a strong ionizing field around it, radiation that might disrupt dust molecules. So the short answer is we don't know, but we're going to find out.
So would presumably as you get more data, you'll be able to extrapolate that information better, and we'll be learning more about the nature of the dust.
Yeah. And it's possible that some galaxies are completely invisible at short wavelengths due to dust absorption, but that heats up the dust, and that then radiates at very long wavelengths as thermal radiation. So there are various other telescopes that have been active over the years, like Herschel, which is a space observatory, ALMA, which is working now in Chile, that might be able to see that.
Okay, if I can follow with another related question, and that's the on the break. That is a hydrogen line, presumably, more than one line.
Yeah, that's right. So that's the to the first excited state, then equals 2 level. That's where the recombination line series converges. So that's an edge effect. So that produces the break rather than a single emission line.
I've got a question, Andrew. It seems like often the theorists will come up with a limit for how far back in the past they think the first galaxies, or indeed the first stars, should be. They should be X number of thousand years after the Big Bang. And then the observations come in and we get older ones that are expected. There seems to be a history of that. Where is that going to end, do you think? What's your
Well, I think, I mean, you know, we're scientists, so theory certainly has a role to play, but I think it's still an observationally driven field. It's so difficult to simulate the formation of stars using a computer because you're spanning a range from the quantum level to the size of a star, right? And no simulation can accurately represent that. They put in a lot of assumed physics, and observation is very important in tuning that up. And then your point about finding older and older stars. I mean, when I started my career in astrophysics, the size and age of the universe wasn't known to a factor of 2. You know, the so-called Hubble constant was highly uncertain, and people favoured quite a young universe. So when people found galaxies or stars which were 12 billion years old, that was older than what people thought was the age of the universe then. We now know, thanks to dark matter and dark energy, the universe is a lot older. But that was an example of the theorists saying, oh yeah, you're not going to find anything older than 7 billion years because that's the age of the universe. And then astronomers, observers did. And that pushed, you know, it's not simply a competition, it's an endeavour to understand the universe.
David?
The earliest stars that formed were pure hydrogen and helium. Were also, as I understand it, very massive.
Yeah.
Did they, in their life, synthesize heavy elements in the same way that massive stars do?
Yeah, so in fact, the heaviest stars would have made proportionally more heavy elements. So our own sun will stop when it fuses to carbon, but a heavier star will stop when it fuses through to iron. And yes, it's a good point. They are believed, but again, on the basis of simulation, we might be able to observe this directly. The first generation stars, rather than being about the mass of the sun, might be 10 or 100 even times the mass of the sun. And there's a technical reason to do with that if you don't have the heavy elements, there's cooling radiation to do with the lines of the heavy elements, and it's to do with the gene's mass of the early objects. But this is all theoretically hypothesized, but you know, we want to keep them honest and find it in reality. So I think there's one
Right at the back here.
Yes, thank you. I don't know if it was implied by your list of questions or answers that you hope to get from the Hubble, but one of the big, sorry, not from Hubble, from James Webb, but one of the big questions from this sort of stage cosmology is which came first, the chicken or the egg? So is it the population of free stars, is it the supermassive black holes, or is it the galaxies, including maybe dark matter galaxies?
Yeah, so I think the paradigm is that early on in the universe there's fluctuations, we can see those in the cosmic microwave background, and then over time, over millions of years, those slight fluctuations in density caused dark matter to collapse in, and then ultimately the gas to collapse in. So those slight overdensities grew and grew and grew. Eventually you have a threshold of gas density such that the first stars trigger. So it depends what you call a galaxy, but there will have been overdensities of gas, big overdensities of gas, which ultimately became galaxies, and then within that stars would form. The central supermassive black holes, that's an open question. So it's possible that the initial seeds for that were the very early stars that ended their lives as black holes, and then you got some terrific merger of a lot of these. The other hand, there's a theory called direct collapse black holes, where essentially you skip the star forming part and you just get, you know, a black hole forming directly. Those have been hypothesized but never seen. So again, it's great fun. I mean, you know, we know black holes exist. how did you seed the first ones that went on to be 1 billion solar masses? At the moment, we don't know.
Is that something James Webb might be able to answer?
Yeah, I think so. If we're able to see early episodes of star formation, we might also see evidence for these direct collapse black holes. So, possibly.
I'll read a question which has been put on the YouTube stream. Stephen Brooks has asked, what length of observation has to be made of objects to get sufficient information to begin the analysis that you undertake?
Yeah, that's a very good question, Stephen. So the spectra that I showed you are about 30 hours duration. So that wasn't a single observation. You split it into sections. The reason for that is things like cosmic ray strikes you want to average out over. But it's about 30 hours integration time. But some of the brighter galaxies you can get away with much shorter. And in fact, people who are studying transiting planets, their objects are so bright they use the shortest possible time repeatedly so that the detector doesn't saturate. So it depends exactly what you want, but a few tens of hours are currently the most sensitive observations.
So it's like amateur observations, really. Some objects take many, many hours, and some a fraction of a second.
That's right.
Yes, Ken.
This James Webb Telescope, is it in a stationary orbit?
Yeah, it's in the Lagrange 2 position. So this is, if you imagine the Earth-Sun system, there's actually 5 points where the gravity of the Sun and the Earth approximately balance, and L2 is one of them. And it means that it's quite a stable orbit. You don't need to waste a lot of propellant station keeping. And the Sun, the Earth, and the Moon are all always on one side of the spacecraft.
Around the moon, is it?
It's beyond the orbit of the Moon. It's about 1 million either miles or kilometres. I'm going to say miles away. Yeah.
Yeah, so it's in orbit around the Sun, but not around
That's
the
right.
Earth.
Yeah.
Any more? John Rogers.
Maybe I missed if you said this, but are all the high redshift objects you observed so far gravitationally lensed objects?
No. But it's very good. I did not mention that. The first spectrum I showed, the Joe Biden one, that was a gravitationally lensed object. But the 4 that we published just before Christmas, they are in and around the Hubble Ultra Deep Field, so they're not, at least to the best of our knowledge, magnified by foreground objects.
And on this side, yes, Alan.
Just a question on the cosmological constant. With the new discoveries and going sort of higher Z numbers, is that giving us a more accurate measure of the constant? Because I understood there was a little bit of a
Yeah, so there's a mystery or tension at the moment. So there's the Hubble constant, which is the expansion rate of the universe today. Now it's badly named, it's not constant at all, it was a different value earlier in time. There's several different ways of measuring it, but they slightly disagree. One is from the cosmic microwave background, another one is from using supernovae, exploding stars as standard candles. And it's thought that if that discrepancy is true, and it's not just some bias or observational error, that there might be some new physics there. James Webb might help this slightly because it will be able to see supernovae at greater distance. What it will help a lot with is understanding the acceleration of the universe, which is a mysterious dark energy, which was not at all expected and was discovered around 2000, for which that team received a Nobel Prize. So we've known for 100 years the universe is expanding. We did not expect it was accelerating. So I think it will nail that a bit better. But there's another big facility coming online soon, which is the Vera Rubin Observatory, previously called the LSST. This is a big ground-based observatory in Chile. And James Webb has quite a small field of view. It's a few arc minutes. Vera Rubin has a field of view of square degrees of a shot, and that will find a lot of these supernovae explosions out to big distance. The reason why we won't find them with James Webb is our patch of sky is so small, the chance of finding one is low. But we can follow up things that other telescopes discover. And getting more supernovae at greater distance, that's going to address things like dark energy.
I've had a question on the YouTube stream from Richard Miles. He says, can you say anything about globular clusters or their equivalent associated with the very distant galaxies?
Yes, yes, Richard. So people are interested in globular clusters, which are very dense and very old clusters of galaxies seen around our Milky Way and indeed around most massive galaxies. So there's a belief that we should be able to see the formation early in time of these globular clusters. There's a claim actually in gravitationally lensed galaxy that this, a protoglobular cluster formation has been seen. So yeah, we're very keen on globular clusters. What exactly their relation to galaxies is interesting and unclear, because some of the globular clusters around the Milky Way are actually older than the Milky Way. So were they surrounding the progenitors of the Milky Way, and we inherited them when they merged? All this sort of stuff is not yet understood.
And there might be galaxies that have just lost their spiral arms.
Yeah, but they're very compact and dense. I mean, I think, if we found a lone globular cluster, we call it a galaxy for short, right? I think the early phases of globular cluster formation are very interesting and unconstrained. But I think JWST should, possibly will enlighten us.
Can I ask another question?
Yes.
What do we deal with? Do we deal with light years or parsecs now?
So typically we work in parsecs, but often we work in terms of redshift or look back time.
So it's parsecs is the number one.
Yeah, professionals tend to use parsecs in their literature.
Yeah. Of course, if we were true scientists, we will be using meters. But yeah.
Right, any other questions? At the middle back here.
Can James Webb help our understanding about inflation?
About what?
About inflation.
Inflation.
Yeah. I think not directly. So the experiments which are shedding light on that are things that study the cosmic microwave background, and that tells us the fluctuations of matter density very early in the history of the universe. James Webb, the furthest that we will be able to see is within a few 100 million years of the Big Bang. So that's a long time after the inflationary epoch.
Any more? What? Yes.
Can I just ask another one? This goes back to, I'm always intrigued that professional cosmologists do use parsecs instead of light years. Because light years is a much more useful one. If you say something's 10 billion light years away, you know it's 3 billion years after the Big Bang.
Yeah.
And if you say 3 billion parsecs away, well, I'm going to go, well,
Yeah.
it just seems much more intuitive, light years.
Yeah, but in a way, distance to us seems very intuitive, but in fact, in astrophysics, so if I say something is 10 billion light years away,
Like a couple of years.
what does that mean? So if I froze the expansion of the universe and sent a photon from that distant galaxy to us, that would take 10 billion years. But of course, the universe is still expanding. So now that galaxy is actually further away than that distance. I teach a course on cosmology, and distance is actually very confusing in an expanding universe.
So traditionally the parsec was the thing that you could actually measure, because it's the actual displacement of the parallax, so it's an actual measured quantity. There's no theory there that requires a leap of faith to. But that's not really the case when you're dealing with very large distances, so you can't measure the parallax.
But all of them are 0 point of the sun, so it's parsec is 0 point of the Earth-Sun distance, right? And the year is obviously 0 point of the orbit of the Earth around the sun, so it'd be better if everybody used a unit that didn't depend on the Earth, right?
Perhaps we need an agreement from the International Astronomical Union to rule what that unit should be, or come up with a new one.
I'm not sure.
A new metric. Yes, that's Bill has a question.
Thank you. Does it shed any light on the conflict between dark matter and modified Newtonian dynamics?
Potentially. So I mentioned briefly looking at the kinematics of galaxies using the integral field. So that's the rotation curve. And we observed that the rotation curves are flat. That probably doesn't mean anything to anyone, but what that implies is there's a lot more mass in these galaxies than we can see in the form of stars. And this was one of the early evidences for dark matter. And people study these rotation curves in great detail, and people speculated that you could explain it if you changed gravity. So gravity we call an inverse square law force. You know, if I'm twice the distance from an object, the gravity is a quarter of the strength. Yeah. If it falls off as a different power law, people claim that might explain the rotation curves, but nobody's really been able to do it properly. And there's other observations in astrophysics which negate that. So my money is still on gravity being right and dark matter being right. But it pays to keep an open mind. These modified, they're not cranks. They are, you know, finding another plausible explanation to fit the data. But then, to my mind, what is more plausible? We don't know what dark matter is, but we keep on finding new particles. So, new particle. We've known about gravity for quite a while. Tinker with gravity, that's a bit more ambitious.
Right, well, I think we've quizzed you on quite a wide range of subjects, most of which is very little known about. So, thank you very much, Andy, again. We're a bit early for the tea break, which is supposed to begin at 1400, so you can just mill about for the moment. And we will start again at 16:30. So, ladies and gentlemen, we will recommence. Please take your seats. You'll see on the screen we've got details of the Winchester weekend, so there's still a few places available for that. So book up through the website or by phoning up the office, or you could even try sending a letter, but it probably won't get there soon enough. So I don't recommend that. Apologies for the late arrival of the December journal. That was mostly due to external circumstances. But we hope to get the journal out much quicker in future. I've also been reminded that we've got some public observing in the West of London Astronomical Society, 24th to the 26th of February, and that is in Ruislip Lido in West London, which is quite a dark site for London. So if it's clear, we'll be doing public observing 24th to 26th of February, and details of that are on the West of London Astronomical Society Wallace website. Next, we have a Zoom presentation from, if I'm saying it wrongly, apologies, Javier Peralta. Now, Javier was born in Algeciras, Spain, and he graduated in physics from the University of La Laguna in Spain in 2003, specializing in astrophysics and applied physics. His PhD research focused on atmospheric dynamics of Venus using data from the Galileo and Venus Express missions. His supervisor was Ricardo Hueso, who is a well-known collaborator with amateur observers, and and Javier is very keen to collaborate with amateurs on studies of Venus. He's been employed by the Japanese Aerospace Exploration Agency, or JAXA, from 2015 to 2020, and they, of course, sent their probe to Venus. And he's now employed by the University of Seville, the JAXA probe is called the Akatsuki Venus Orbiter, and Javier is on the science team of the Akatsuki, saying that wrongly, Akatsuki Venus Orbiter, and he is studying the cloud dynamics in Venus's atmosphere. I talked to him, at the European Planetary Science Congress in Granada last September, and I talked a bit about amateur observations there, and he asked me what the best way was to get in touch with British amateur astronomers, and I said, well, through me, and can you give us a talk? And we could do it by Zoom, so that we can do a remote talk. So that's what we're trying to do. So he is in Spain, and let's see if we can get Javier here to talk about ProAm collaborations in the study of Venus. Are you there, Javier?
Yes, thank you so much. You pronounce very well my name, don't worry. Thank you so much.
Right.
And it's great. I'm really happy for being invited to give a talk to you.
Right, well, you may begin then.
Okay. So, yeah, the main goal of this talk from my side is try to invite as many of you to participate in the Venus observations that are normally organized in coordination with a ground-based observation from Mauna Kea, from IRTF, and also from Akatsuki, and to convince you to observe the so difficult planet of Venus, that I know that is not the most attractive to many of you that maybe prefer Saturn or Jupiter to observe. And I would like to show some of the main outcomes of some fruitful collaborations that we have maintained with some brave observers around the world that have collaborated with us. And of course, to understand why Venus has become in the last year so attractive for many amateur astronomers, I would like to highlight some of the main outcomes from Akatsuki that have discovered important features that can be visible now with ground-based observations using a near-infrared wavelengths, also taking the chance that many of the CMOS cameras that are being sold are sensitive to near-infrared wavelengths where we can see very interesting details. So, okay, I will advance. Okay, so just a brief presentation later for the planet Venus, although I am pretty sure that most of you know most of these details about the planet. Venus, as you know, is the second planet in distance to the Sun in the solar system, and Venus and the Earth are very similar in many aspects. They are similar terrestrial planets regarding their size, their density, their composition, and we could even say approximately similar distance to the Sun. But they also keep very important differences relative to some critical aspects that have to be not also regarding their climate, but also the atmospheric dynamics. In the case of the CO2, both planets have a similar amount, but the key difference have to be in how the CO2 is stored in each planet. In the case of the Earth, the CO2 is dissolved in oceans and also in carbonates, while in the case of Venus, at some point, it was completely released to the atmosphere, to the point that the atmosphere is more than 95% of CO2. Also, compared to the Earth, the axis rotation of Venus is reversed 180 degrees, and also the rotation period of Venus is radically different to the Earth. The period of rotation is about 443 terrestrial days against the 24 hours of the Earth, and this makes Venus a very interesting planet to study for people who like meteorology because Coriolis effect does not apply, and the atmospheric dynamics change drastically. Also, Venus has a really thick layer of clouds. These clouds are mainly composed of sulfuric acid droplets, and what is important about them is that they contain an unknown absorber in ultraviolet wavelength, and this absorber is radically important to understand Venus in many aspects because it is able to absorb about 50% of the incident sunlight. So this absorber is very important to understand the greenhouse effect of the planet, the atmospheric dynamics, of course, and as you see, the mental health of researchers, because unfortunately, we have more than half a century of research without knowing which is the observer behind the nature of this observer. And if you compare the thermal profile of the terrestrial planets of the solar system, Venus, Mars, and the Earth, you will see that for lower altitudes, the thermal profile of Venus shoots to very high temperature of more than 40 degrees at the surface. And another important difference has to be with the altitude of the clouds that are between 60 and between 50 and about 70 kilometers in altitude, much higher altitude than the clouds in the case of the Earth. And also, it is important to consider about Venus is the greenhouse effect, that in this case is a runaway greenhouse effect, in which the atmosphere is able to retain most of the thermal emission from the hot surface, and made it return back and heat the atmosphere and the surface so much that we have these hellish temperatures. As that what makes the Venus the hottest planet in the solar system, in fact, hotter than even Mercury. And Venus, for people who study atmospheric dynamics, is very interesting because they have a very complex atmospheric circulation. Most of you have heard about the atmospheric superrotation of Venus. This superrotation dominates between the surface up to the cloud tops that are about 70 kilometers in altitude. But in addition to this superrotation with winds that move really fast to the west, we have at higher altitudes another type of circulation that is called solar to anti-solar circulation, going from the midday to the midnight. And between these two regimes, we have a complex region, what we used to call transition region, where the superrotation transits to the solar to anti-solar circulation. And it has associated the very complex dynamics that we are now trying to start to characterize. During Venus Express, we tried to see the motions of this transition region using images of the oxygen airflow on the night side. And but for the moment, we have to increase the amount of data to characterize the dynamics in this interval of altitudes. So about the superrotation, that is also the main topic for the Japanese mission Akatsuki. It makes the atmosphere of Venus to rotate very fast, so that instead against the 243 days of the solid body of the planet, we have an atmosphere that is able to rotate to make a full revolution in 4 days. This is 60 times faster than the surface. And this superrotation is based on a balance of inertia caused by a complex transport of momentum and energy due to different factors. On the one hand, for example, we have a meridional circulation on Venus, that this meridional circulation moves the atmosphere from the equator to the poles. So this meridional circulation is able to extract momentum from the equatorial region up to higher latitudes. But since the superrotation is still very strong at the equator, we need to have other agents transporting momentum in the opposite sense. And this is why we have been studying the role of the thermal tides that are caused by the kind of waves that are caused by the periodic heating of the sun. Also, other planetary scale waves, and also atmospheric instabilities and turbulence. So we have kind of complex puzzle here that we are trying to understand for a long time. And during the Akatsuki mission, we realized, thanks to the data from one of the cameras, the UVA camera, that the solar tides seems to have a very important role in explaining the superrotation. I will come back to this later anyway. Concerning the remote sensing tools that we use to study Venus, as many of you know, it happens also not only for Venus, but for other planets of the solar system. Depending of the wavelength we use for studying or observing the planet, we see a different planet with different physical processes and different altitudes. In the case, for example, of the scattered radiation from the sun, we can infer different information about the planets. For example, we can extract information about the type and size of the aerosols. We can also infer the abundance of these aerosols, calculate also using relative transfer models their vertical distribution. And when these wavelengths are able to arrive to the surface and they are reflected on the surface, we can also get information about the topography of the planet. One example of a scattered light on Venus, and also observed in this case, has to be with the different levels we can study on the day side, depending on the wavelength. We can say that we have 4 bands to study the day side, the clouds on the day side of Venus. One band is close to 280 nanometers, where what we have dominating is the absorption from the SO2. And this SO2 is distributed in different altitudes, not only in the cloud tops, but even a bit above. So thanks to our studies with Akatsuki, we were able to see that the dynamics of the SO2 are a bit different to the dynamics that we can see from the unknown observer. Also, between 316 and 400, we have the region that is dominated by the unknown observer. This is the wavelengths that many of you have used to observe Venus with small telescopes. Unfortunately, because of the atmosphere of the Earth, the band of 280 normally is difficult to use because we have a lower transmission in our atmosphere. But at the same time, we can also observe the middle clouds, the clouds that are a bit deeper than the upper clouds, using both visible and near infrared wavelengths, visible between 570 and 680, and in the near infrared between 900 and close to 1 micron. And another example of scatter radiation, as I told you, have to be with the reflected, that reflected of the surface. And I will also go back to these two later. And from the refracted radiation, we can also get information. Normally, we use radio occultation experiments to emit radio signals from a spacecraft to the Earth. This radio signal, normally we make the emission so that they get through the atmosphere of the planet, and the signal is bended and then arrive to the Earth. Depending on the angle why this signal is, how this signal is bended, and how retarded is the signal, we can infer some physical parameters, like for example the temperature of the atmosphere. And also concerning the absorption of the radiation in the atmosphere, we have the stellar occultation experiments that we can do not only using probes but also ground-based observations, in which we can observe the spectra of a star, and then we observe the same star later when it's being hidden by the atmosphere, and then the light of the star have to get through the atmosphere of the planet. And through the difference of the spectra with both observations, we can not only identify absorption lines and different components of the atmosphere, but also calculate the atmospheric transmission of the planet. Finally, we can also study the emitted radiation. That normally for this we use the night side of Venus. We have different wavelengths to study different atmospheric parameters at different altitudes. And two nice examples have to be upwards. You see images of Venus taking with the one gray scale, taken, for example, by the Parker Solar Probe during the third flyby they made in the 11th of July of 2020. And these observations were really unexpected, because this camera they use for observing Venus can see mainly in the visible and close to near infrared. And unexpectedly, we were able to observe the thermal emission of the surface. As you can see, how well is correlated the grayscale image with the one of radar from Magellan mission. So we can use some wavelengths closer to the visible, and yet we can observe through that window the thermal emission of the surface of Venus. Also down, you can see the infrared radiation, the thermal emission, not from the surface, but from the upper clouds of Venus, that they are cooler. Normally, for observing this infrared radiation from the clouds, we have to use longer infrared wavelengths at 3.8, 5, and also close to 10 micron. That these are wavelengths that are yet to hard to be used by the ground-based observers unless you use cameras that are sensitive to these infrared wavelengths. Another example of type of observation of Venus, in addition to the thermal emission, has to be with observing the thermal emission from the deeper atmosphere, but when this thermal emission is partially blocked by the clouds. So in this kind of observation, we observe the transparency of the clouds. It's the case of the deeper clouds of Venus that are able to partially block the thermal emission from the deeper atmosphere at the surface. And then we can see their contrast through this thermal emission, and we can then see their motions. So this is the opacity of the clouds, or the transparency of the clouds, of deeper clouds, are used to see these lower levels, and also help us to see their motions and study their dynamics. So is in a summary of what I have been explaining, to measure the winds on Venus, we can use different cloud levels and different parameters so that we can try to characterize this atmospheric superrotation in 3 dimensions. Using, for example, ultraviolet on the day side for the cloud tops, then near infrared images on the day side for the middle clouds, and finally the deeper clouds, the lower clouds, that can be observed not on the day side but on the night side using longer infrared wavelengths. In this case, the transparency of the cloud, or the opacity. So, concerning these infrared observations, how the Japanese Akatsuki mission has made a small revolution for the observations, and in which way have provided new ideas for ground-based observers to make observations of Venus. Some of you maybe know that the Akatsuki mission was scheduled to make the first orbit insertion in 2010, but unfortunately there was a problem, and the Akatsuki spacecraft was lost for a time until it was recovered and was able to make the orbit insertion in 2015. What happened in December of 2010 was the drama of Akatsuki, in which there has been even some manga. What happened is that we have the unexpected formation of a kind of salt that blocked one of the valves in the main thruster and destroyed it completely. So the spacecraft was not able to reduce the velocity before making the first orbit insertion, and then it did basically a flyby of the planet. And for 5 years after this, the orbiter was orbiting the sun, and the Japanese people were thinking very hard how to recover the spacecraft when the main thruster cannot be used. Fortunately, there was a successful strategy to recover the spacecraft, and we were able to make this orbit insertion in 2015. So, the Akatsuki mission is very special because it was particularly focused in studying the superrotation at observing Venus different filters to study different levels of the clouds, as I have explained before. Of course, it has some other cameras that were also meant to study other phenomena, for example, like the lightning, but mainly the atmospheric dynamics. So in the case of the infrared, we have 3 instruments, IR1, IR2, and LIR. And these cameras have basically are observing Venus in different infrared wavelengths to study different levels. Just for you to have an idea, the idea of the superrotation we had before 2016, that was when the nominal observation of Akatsuki started, was something like this. So you see in the columns on the left the day side of Venus. On the right you see the night side of Venus, and then the upper row is for the upper clouds, and the lower row is for the deeper clouds. So what we have before 2016 was that in ultraviolet, in the upper clouds of the day side, we have a very good characterization from not only ground-based observers, but also several space missions. In the case of the deeper clouds in the night and the day, we have some profiles, isolated profiles from different flybys, also from Akatsuki, but Akatsuki covering only, sorry, from Venus spread, but covering only half of the hemisphere, one hemisphere of the planet. And in the case of the upper clouds of the night side, that normally these are the images we used to make to use the thermal emission of the clouds. We only have a profile for the polar vortex from Venus Express, and the reason for this is that in low latitudes we didn't see anything. It was difficult to see anything on Venus. So, but this is what we had before Akatsuki. After 2016, both thanks to the Akatsuki and some revisit of data from one of the instruments of Venus Express, then the situation changed. For the deeper clouds, we have more complete profiles, as you can see. And for the night side upper clouds, I want you to pay attention because here the profile is very weird. We have a kind of dispersion in the wind speeds, okay? I'm going to show you, make a zoom here so that you see. You see in colors the wind speeds on the night side upper clouds as measured with ground-based observation, in this case with Venus Express. And in comparison, we have the black profile is the one from Galileo of the day side of the super rotation. And some of the measurements, the one of cyan color, they seems to match well the fast speed of the super rotation. But at the same time, we have the red color, the red measurements of passive thrusters that have some anomalous values of speeds. Some of them are really, really slow. What we discovered at the time is that, not always, but at some moments, it seems that the super rotation became chaotic on the day of the night side, upper clouds. And we have some kind of changes in the winds that were completely unexpected and completely unpredicted by the general circulation models. And also for Akatsuki, another important discovery for the upper clouds has to be with the meridional circulation, because classically what we understood about the meridional circulation on Venus is that the winds went from the equator to the poles, but with Akatsuki, when studying the night side, they discovered that it is reversed. So in the case of the night side, it seems that the meridional circulation goes from the poles to the equator. Okay, also something unpredicted by the circulation models at the time. And we also discover by comparing observation from long time, from the end of the 70s up to date, that the wind seems to be changing along the time in the deeper clouds and also the upper clouds. As you can see here, we only isolate and put also the in situ and the wind measurements from the space missions. And this variability seems to be similar to the one seen by Katuntsev and other authors for the cloud tops. And more importantly, if you see here in the yellow profile, it seems that the winds are increasing at the same time that Venus is becoming darker. So here you can see a study of our colleague from Korea, Junju, in which she discovered that the albedo of Venus seems to be decreasing along the years. So this means that the unknown absorber might be increasing its abundance. And if the unknown absorber is becoming more abundant, it might be absorbing more energy from the sun and making the super rotation to become faster. So as you see, a decrease in the albedo seems to have a correspondence in an increase of the wind. And also, finally, concerning the infrared observations, two important discoveries that have also translated in some motivation for amateur astronomers. Ones have to do with the stationary waves. We have detected for the first time some patterns that do not move in the middle of the super rotation. These are waves that are excited at the surface elevations. We have discovered this independently with Akatsuki and Venus Express. And we have also observed plenty of vortices and instabilities, and this is really surprising because in a planet with no Coriolis effect, we don't expect these shear instabilities to be so abundant, but we have them. And we have a special case from ground-based observation in which we were able to discover a giant vortex, very big, as you can see. Was observed for about 1 month. And this is not very frequent, but we know that maybe it can happen once every 15 or 20 years, because you can see another phenomenon similar to this in the legacy data from IRTF. And finally, and this one of the favorite reasons for the amateur observers, as I will show now later, we also discover a giant wave in the deeper clouds, a kind of discontinuity. I don't know if you can see here from the images. This discontinuity, we can observe them in the deeper clouds of the night and also the middle clouds of the day side, and it moves faster than the superrotation. And what is funny is that this discontinuity seems to be on Venus since the observation of the 1980s. So we have been missing this phenomenon for several decades until the higher spatial resolution of Akatsuki allowed us to see it more clearly. What we know about the discontinuity is that this wave seems to be excited deeper below the clouds, and it is able to propagate up to the middle clouds, but we have never been able to observe it in the cloud tops. So in ultraviolet images, we didn't see the discontinuity. That makes us think that the discontinuity is dissipating before arriving to the cloud tops and probably providing momentum to the superrotation. So this is the scenario we have with after the Akatsuki mission. And here in this moment of the talk, I would like to show to you some examples of some fruitful collaborations between amateur astronomers and the Akatsuki mission. First of all, there was a kind of beginning during the Venus Express mission. In 2007, there was a flyby of the emission to Mercury called Messenger. And this Messenger probe makes 2 flybys of Venus, one of them in June of 2007. And at the time, there was a big campaign of coordinated observation from different observatories, since we had 2 spacecraft observing Venus at the time, Messenger and Venus Express. Among them, one of the amateur observers that was providing images was Damian Pitch. He took very nice images of Venus. And we also using this work in combination with the data from Messenger to calculate the atmospheric dynamics during the flyby of Venus on both the day and the night side. This work is very beautiful because combining different techniques for measuring the winds, we were able to obtain what we think is the most complete 3-dimensional view of the winds of Venus on the day side and the night side, covering from the clouds to very high altitudes, close to 120 kilometers, using Doppler winds. And you can see here some combination of the winds. In the case of the day side, here on the left, you can see some of the measurements from Messenger and also from the images from Damian Pitch. In the case of Akatsuki, we have different filters to observe Venus, and ultraviolet, visible, near infrared, and I showed to you here the comparison with the range that is usually covered by amateur astronomers using commercial filters. Normally, they cover up to 1 micron, although lately the CMOS cameras are sensitive far beyond 1 micron, and we have been used this as an advantage to sense, for example, the surface of Venus, as I will show later. We have a website that, needs to be updated, that we have used it for collaborating with amateur astronomers. In this website, you can have access to the programmed observation from Akatsuki, the geometry of observation, and the type of observation we're going to make. you can also get information about the exact time where the cameras are going to take images. For in case that any of you wants to collaborate by complementing these observations or making simultaneous observations of our similar areas when it is possible. The first nice work about the winds of Venus was made by Agustin Sanchez La Vega, was also my PhD supervisor along with Ricardo. And we take the chance to measure the winds of Venus right before the arrival of Akatsuki in 2015 to see which was the condition of the winds of Venus at the moment before Akatsuki started to measure. Here you see the wind profiles at the time that were one of the most accurate published for the wind speed using ultraviolet images of very high quality. But time after, I accounted with the help from Emmanuel Cardassis, and also from some Australian observers like Phil Miles and Anthony Wesley, and they helped in this work for studying the middle clouds of Venus in near-infrared wavelengths to study the cloud patterns. Here in this image, you can see that the panels J, K, and L, they correspond to amateur observations. The other are observation of Venus using the IR1 camera. Okay, as you see, they are very useful. Their quality allows us to study also the cloud patterns that we discovered that they can change from a kind of turbulent to more laminar patterns. Oh, sorry, okay, now it's advancing. More laminar patterns. And we also observe that also amateur observers have also detected this, that for reasons we don't understand yet, the northern hemisphere becomes darker for the middle clouds sometimes. During some periods are ranged between 4 and 5 days. And we also observe some sharp darkenings of the albedo that are able to decrease between 1 and 4%. And more rarely, we see some hook structure that has been observed also in 2022, by the way. And more rarely, waves. It's very weird to observe waves in the middle clouds, but from time to time we can observe them, and then we have some images reporting them. And in addition to study the cloud patterns, the amateur observers have helped us to complete the wind profiles. In this study, for example, the IR1 camera failed completely and could not be used after December 2016. And from then, Emmanuel Cardassis was provided images to study the winds. As you can see in the profile here below, the light pink observations are the ones from amateur observers in this work, that they are consistent with the measurements taken done with Akatsuki images. And here you have Emmanuel Cardassis, that he is very enthusiastic. When we reported about the discovery of the discontinuity, and we told that discontinuity could be also observed in the middle cloud, then he said, "Oh my God, I have filters to observe the discontinuity, this level of the clouds. Do you think that I have chances to observe the discontinuity?" And I said, "Oh yeah, this is very big. It should be possible." And in fact, Phil Miles have been also being successful to observe the discontinuity. And then during one of the hardest moments of the pandemic, at the beginning of the pandemic, he coordinated with other observers to observe the discontinuity at the beginning of 2020. And we published a work that has been awarded by the Federation of Astronomical Societies of Spain. So in this study, we studied the discontinuity, we measured the period of rotation, the orientation, the latitude, and what is important, we discovered that the period of rotation had speeds that are between the upper clouds and the middle clouds. And this is consistent with a wave that propagates with faster velocities in the middle clouds, but will vanish at some point before arriving at the upper clouds. So this work was very, very nice. Also, he made a comparison with the Y pattern of the ultraviolet images, and we didn't see any kind of corresponding with the discontinuity and the Y feature. And more recently, in 2022, we have made an even longer campaign. We have been able to observe Venus with the middle clouds during 140 days with amateur observations. And thanks to this, we have observed the discontinuity again with a small telescope. with images taking most of them from Portugal, but also from Italy. And you can see some events of the discontinuity that we have identified in 2022, last year. And more importantly, it seems that we have observed the discontinuity for the first time in ultraviolet. I don't know if you can see this animation. The discontinuity seems to have shape for several hours, appear manifested in the ultraviolet images from Akatsuki, and then disappear. At the same time, the discontinuity was visible in the middle clouds. So this might be the first report of discontinuity being able to propagate to the cloud tops. And we think that this is because the winds in ultraviolet images have become slower during this period of observations. Finally, these are some works that we have published with amateur observations. I would like to give some ideas for new observation with small telescopes that I hope they are welcomed by you or interesting. First will be to collaborate in the next campaigns of observation from IRTF, where we usually observe the night side, but we cannot observe the day side. And these observations are very interesting because if we see the discontinuity on the night side, it will be interesting to check if it is able to be observed in the middle clouds of the day side. And at the same time, we need more ultraviolet images to study the winds, to see if how is the long-term cycle of the winds, and if they have a correspondence with the variability of the albedo, and also to study the waves that, as you can see, in some images from small telescopes can be observed and they can be characterized with no problem. Also, Antonio Sutadao has been making tests with new filters in near infrared to see which have the better contrast. In fact, he discovered that the Bader-Sloan ZS is the one that have provided better result for obtaining optimum contrast for observing the middle clouds. So you can take the chance to buy this filter if you want to observe the middle clouds of Venus. Just to see an example, thanks to the higher contrast now with this filter, we can observe much better the motions of the clouds, and we can even characterize the winds, not only observing the cloud discontinuity. And more recently, Phil Miles and Anthony Wesley, they have been for several years combining two filters to isolate the band at 1.02 micron for observing the thermal emission of the surface in search of possible changes on the surface, maybe related to volcanic activity, we don't know. And what is more important is that during 2022, we compare observations of the lower clouds from IRTF with the ones from Phil Miles of the surface. And Phil Miles was obtaining signals not only from the surface, but also from the lower clouds. It happens with this, we know this from Venus Express and Akatsuki mission, in that in bands where we expect to observe the surface, sometimes we don't observe the surface. What we observe is the opacity of the lower clouds. So we can use filters close to 1 micron to observe not only the surface, but the motions of the lower clouds. And we want to use these new observations to try to estimate for the first time the winds of the lower clouds using 1 micron filters. Another interesting idea, taking images in combination with Akatsuki that have higher spatial resolution to try to train neural networks for try to see if we can better correct the atmospheric turbulence of the images. And another idea is trying to do spectroscopy and photometry of Venus. Many of you already know the diffraction grating star analyzer 100 that has been used by Christophe Pellier and some other observers. And finally, trying to make stellar occultation when it is possible. In fact, I provide here a prediction of a stellar occultation by Venus in this website that you can use as a reference. And finally, some of you are not aware, we have discovered recently an asteroid called 2021 PS27 that has an orbit that intersects the one of Venus. And this asteroid have the shortest orbital period known for asteroids in the solar system. So the period of orbit is 114 days. And the team that discovered this asteroid has predicted that it might get close to Venus in certain dates, and we have the chance to observe impacts on Venus from ground-based observations. So you have here visibility from Earth. You have the 7th of June of this year. You have a moment in which you could try to observe the night side of Venus and try to see possible impacts on the night side. And the next favorable time for this asteroid being close to Venus is the 5th of July of 2026. But in any case, if you are interested more to clarify this observation with better detail, I can help you to get in touch with the main author of this work. So this is all. Thank you so much. And if you have questions, please feel free to make them. Thank you so much.
Thank you very much, Javier. More very up-to-the-minute stuff. Well, do you know, Javier, that we have a Mercury and Venus observing section, and it publishes a newsletter. Did you know that?
Well, can I,
yes, I know about that, yes.
can I make a comment?
Yes, Paul, who is our Mercury and Venus director, will make a comment.
So, Jeremy, very interesting talk.
Can you hear Paul, Javier?
Can you hear me, Jay?
Yes, I can hear Paul, yes.
Okay, so very interesting talk. A lot of the ideas you put at the end of the talk, we've been doing for the last 5 years in the Mercury and Venus section. And we've been publishing data about the Akatsuki spacecraft observations correlated with amateur observations. We've got a paper due out in the journal in February, and Richard McKim wrote a good one analysing the observations from 2015 to 2020. I was just wondering, were you familiar with this?
Yeah, I mean, yes, I have not checked lately, so I don't know. Okay, in the last year, I have been a kind of missing, and I didn't check at the time.
Okay, maybe we could have a conversation.
I have to confess that I have been using Alpo Japan sometimes because I am more in touch now with the Japanese, of course, after living there.
Yes.
Yes, but no, but of course, I will check. I will check definitely not for this work that is already under review, but we are planning some new studies of the discontinuity and covering more periods. And of course, I would like to have a look at it.
Why don't I contact you and show you what we've done? That might be easier.
Mm-hmm. Okay.
That. Okay, I'll do that.
Yeah, we can.
Yes, please.
Yeah, we can send you the newsletter as well.
Yes.
Yes, I will be glad to receive them.
Yeah. Okay. And we've also got a meeting in April of when we'll be having some talks about observing Venus as well. So we'll have quite a focus on it, since Venus will be very visible in the next few months.
Yes.
It's now in the evening sky. It's visible after sunset, and the distance from the sun, the elongation is now increasing, and it'll be a greatest elongation in June. So we'll have quite a good period from the UK for observing Venus in March, April, May, June. Any questions from David Boyd, first of all?
There was a lot of material on those slides which went through rather quickly. Would it be possible for a copy of them to be put online that we could?
Yes, I can make a copy for you and upload somewhere if you want, no problem.
Right, yeah, then we could put it, we've got a recording of it, but we could possibly put a copy of
yes, if you want a lighter version, I can make a PDF version of the presentation.
We could make it into a PDF and put it on the website as well. Any other questions? So I actually gave a talk about Venus to to Coventry and District Astronomical Society, Coventry and Warwickshire Society recently, and somebody asked a question about the phosphine that was discovered in the atmosphere and what that means. Do you have a view on that, Javier?
I have been following the debates for a long time. And yes, because there has been a very hot debate about it, definitely. I don't know if I am right about this. You know that there is a private mission to Venus that is going to be launched this year. and they will send a proof to Venus, a descent proof that will arrive at Venus in September, I think, or October. And this descent probe has some instruments to characterize not only the vertical distribution of the particles of the cloud, but I think that they can try to measure the phosphine. I will check, but if I remember well when I read about that, they will try to make in situ measurements of phosphine and other compounds. By September or October is when the descent probe will fall onto Venus, and they will take measurements during about 5-10 minutes, I think.
So we're still very much in doubt about how much phosphine there actually is there.
Yes, of course, as you know, the debate now is not whether there is phosphine. The debate is how much phosphine. And right now, it's, some people say that the phosphine is abundant, and some other that is very scarce. I don't know. This is the debate right now, but it cannot be completely solved until we try to measure more accurately. And maybe this descent probe can help to try to arrive at end to this debate.
Right. Any other questions here? Right. Well, we'll keep up the conversation, and we'll be in contact with you. And thank you very much again for giving the talk, Javier. And let's have another round of applause.
Thank you so much. And any of you is interested in collaborating with Akatsuki or with our observation of IRTF during the next year, please get in touch with me. We can try to assess you for filters and cameras that you can use, and also the calendar more suitable for trying to help us for the new works we are trying to try to carry out.
Right.
And remember that in any work you collaborate with us, you participate, of course, as co-authors.
Right. Well,
okay, of course.
I hope we've encouraged more people
yes.
to have a look at Venus and to give it a bit of serious study. It's an object of great interest.
Okay, thank you so much.
Thank you. Again, we will move on now. We have Nick James, Director of the Comet Section, and he used to be Paper Secretary more than 7 years ago, and does a lot for the BAA. And today he's going to, again, do the honours for giving the rundown on what's in the sky and what we've been observing recently.
So, Simon, do I need to... excellent. Could you put the lights down as far as you can, please? Because there are some kind of fairly faint comet tails in this. Thank you very much. So, yes, as David said, I've been asked to do Sky Notes again. I normally do the Christmas one, but we didn't have anyone else volunteering for this, so you got me again, I'm afraid. You probably won't be too surprised to know what the main topic of Sky Notes is going to be if you've been following the comet that we have in the sky at the moment. But I'm going to start off, as I always do, in the middle of the solar system with the sun. And the sun is remarkably active at the moment. We have a naked eye sunspot. Various people have reported seeing this. Obviously, don't stare at the sun to see the sunspot, but use an appropriate filter, or people have actually seen it in fog and cloud. But it's definitely a naked eye spot. It's just passed over the central meridian. This is the MDI continuum image from yesterday. Yeah, so a big sunspot in just passed over the central meridian, and a lot of other sunspots too. And Peter Meadows provided me with this. This is the plot of BAA sunspot number over the last few years, and you can see that there's definitely been a significant increase at the end of 2022, beginning of 2023. So the sun is definitely worth observing. And we've had lots of really good pictures of it submitted to the BAA. This one from Honor Wheeler on the 15th of January. So here it is, that sunspot, that big sunspot coming over the limb. The sun's rotating in this direction. You'll see This is on the same day by Stuart Green, and what he's got there is some hydrogen alpha images and then images of each of the sunspots. So this is the big one, the naked eye spot, AR 13190, but there are lots of other spots too. So if you do get the opportunity to see the sun during the day, and we've had lots of, certainly down in the southeast of England, we've had lots of sunny days recently. Just depends on whether you're actually at home and able to use a telescope. But even just taking something like eclipse glasses, if you have any, or some solar filter material, just have a look at the sun with the naked eye and you should see this big spot. And it's quite an unusual event to have a spot that's visible with the naked eye. Fantastic picture here by Carl Barron, showing it very close up, showing the solar granulation around the spot and the very large umbra, which has been quite active and quite persistent over the last few days. So you need to look at it in the next week or so, because it will rotate off the other limb if you leave it too long. Moving forward to the 18th, so just 2 days ago, this is James Wakeman's image of it in white light and hydrogen alpha. And the sun, because the sun's getting more and more active now, it's worth looking at every day just to see what's coming over the limb. We still have visual observers. Peter Meadows tries to make a drawing of the sun every day that he can by projection. And here is his drawing from the 19th, when that big spot was right on the central meridian. So it's moved on a little bit now. But the sun is still very active, and we've had quite a lot of flares, and I really like this. This is an animation of a flare by Mattia Piccoli, showing really impressive activity. And of course the sun has been active, and the solar wind has been very turbulent, and we'll see the effect that that has on the comet in a little while. But the solar wind that's coming out from the sun and the coronal mass ejections that come out from the sun flow out through the solar system and affect lots of things. They affect our ionosphere, they lead to auroral displays, but they also affect the tails of comets. Couple of things related to the sun, which I really enjoyed seeing on the website, are pictures taken with this. Now this just looks like a can that you might get a fizzy drink or a soft drink in, but it's a solar can. And you can make these yourself, but you can also buy them. They're not that expensive. And what they are is a pinhole camera containing some photographic paper. So the photographic paper is very insensitive. It's a pinhole camera, so the whole camera is pretty insensitive. But the idea is that you put this up somewhere and forget about it for 6 months. And it basically records the sun over a period of 6 months. So you want to put it somewhere where it's not going to get blown away or washed away. But if you do that and you leave it for 6 months, at the end of that 6 months, you open it up and you can develop the photographic paper and you get some pretty amazing things. And this is a sologram by Alexandra Hart, which I thought was really, really impressive. What you're seeing here is the sun moving across the sky, rising in the middle of the summer, getting very, very high up, in the middle of the winter, very much lower down. And you can see where it's cloudy and where there have been cloud breaks, but an amazing project. I think I looked online and you can buy these cans for about £15, something like that. Buy one, stick it up, leave it to 6 months, come back, and you get a really good record of what's happened to the sun over a 6 month period. There was another of these by Matt Williams. This one is interesting in that you can actually see some of the foreground that's recorded on this very, very insensitive camera as well. So it's a really good demonstration of the fact that the Earth has an axial tilt of 23.5 degrees, which is what causes the sun to be high up in the summer and low down in the winter. It's remarkable how many people seem to think that in the summer that somehow summer is caused by us being closer to the sun and being further away in the winter. And you point out to them, well, how does that make Australia's seasons work? But obviously it's not. It's because of our axial tilt, and this records it really well. So these are becoming more and more popular. and certainly recommend you have a go. I've actually bought one, and I'm going to set one up on top of my garage and see what I get over the next 6 months. All of that solar activity has led to some really spectacular auroral displays for those people who are lucky enough to live far enough north to actually see them. And our Deep Sky Section Director, who used to live in Gloucestershire, has moved up to the Orkneys and has been getting a fantastic view of the auroral display. So this was one of the displays that happened this month. I think this is the 15th, 13th, is it? 13th. Really impressive display from Orkney. And Callum has actually sent me a video as well. So that's a still frame, so that's a fairly long exposure. I think it's a few seconds with a Sony Alpha camera. And when you see these things, if you haven't seen an aurora, you don't really get the impression of how dynamic they are. You know, you see this static picture here, but in fact, aurorae can be really dynamic. They can ripple across the sky in a matter of a few seconds. And so what this is actually in real time, it's fairly slow frame rate. It's about 5 frames a second, I think. But it's real-time video of an aurora taken with a Sony A7 camera and a 20mm, I think, f2 lens. And you can see how it develops. You can see how these beams sort of suddenly develop and shoot up. And that's the amazing thing when you actually see an aurora in real life. It's just how rapidly they can change their shape. So anyway, Callum is really well set up there in Orkney with his cameras. But also we have Dennis Brzezinski, who is up that way as well, in Talbot Ness. So Talbot Ness is sort of between Inverness and Wick, so it's a bit further south than Orkney, but it still gets very good aurora. And Dennis asked me to set up a camera for him. So we've set up this camera, which is on the north-facing side of a garden shed that he's got. And that camera monitors the sky permanently, so Dennis can basically check to see whether there's any aurora without the tiresome thing of actually have to go outside and check every now and again. And when he sees that there is an aurora, he can actually set up his camera. But this camera's been really useful for that. And one of the things it does is it produces a time lapse. Hang on a sec. I said to turn the lights down, but I can't see where the buttons are. That's all right. So it produces a time lapse through the night, and this is an example of what you get. So this is starts off as a rather cloudy night. There's a road here to the north of Dennis's that runs down to the local lighthouse. So Peter will know this. We actually had to put up a shield to blank out the lighthouse. But you can see here, this is the aurora developing through the night. Every now and again, a car drives along this road. And so this is running continually, and Dennis is then able to, if he sees an aurora, he's then able to go outside and actually take a picture. And if he does that, that's the wrong one. I'll get there in a minute. If he does that, that's what he gets. So you can see there's a really significant difference between the video camera, which is going at 25 frames a second, and what you can get if you do a long exposure. But the video camera gives him a permanent record of what's happening and also warns him to go outside. And it's quite nice. I can remote into it as well, so I can watch it too, and I can send him an email saying, Dennis, there's an aurora going on outside the window. Go out and take some pictures.
Do you have any idea what the exposure was?
What of the video?
No,
This, I think it's a few seconds.
30 seconds.
30 seconds.
Yeah.
30 seconds. So this is quite a long exposure. So this will have smeared out some of that detail, but it shows you how sensitive a camera is with a long exposure. It's a fast lens as well. So moving on to the planets, we've just had the talk about Venus, and of course Venus is now coming into the evening sky. It's very, very low still, but this is a really lovely picture that David sent me at 3 a.m. this morning, I think it was, David, of Venus low in the west. And if you do have a clear western horizon and you've got a clear night, it's pretty obvious. It's a very, very bright planet. And Paul has even managed to draw it at an altitude of how high up was it when you made this drawing?
Just above the rooftop, so I had 14 minutes to do it.
So I can imagine the seeing was impressive.
It always is for Venus.
Yeah.
but it wasn't too bad actually, because it was early evening and it was fairly steady.
So Venus is at a fairly southerly declination at the moment, but it will come north, and so that's why it eventually it will over the spring become much higher in our skies and much easier to observe. There's a conjunction which is actually on our website as a challenge between Saturn and Venus on the 22nd. So if you have a clear western sky, get out and see if you can take some photographs or observe that. Venus will be very prominent. Saturn is much fainter, so will be much more difficult to see. As far as the other planets are concerned, Mars has been around for a long time. It's now disappearing over to the west, but people are still getting good images of it. This one by Peter Tickner, taken on the 16th of January, showing quite a bit of detail on the surface. Jupiter, of course, is pretty much past its best now, but Damien Peach and Ian Sharp were in, was it Barbados? Is it that where they go for their? So they'd gone to Barbados and collected terabytes of data whilst they were out there, and have just got around to analysing some of it. And this is something that Damien found in some data from last summer. So that's October, is it? I think. Showing a bright spot on Io. So this spot here, there. Now I spoke to John Rogers, director of the Jupiter section, and it does look like this is real. What it is, we don't quite know yet. We don't have any spacecraft coverage of it, but it's in a region, is it Akala Fluctus?
That's right, yes.
Gosh, I'm amazed I remembered that from your... which is because Io is a volcanic world, rather different to the kind of volcanoes that we have on the Earth, but it's in a volcanic region, and it's possible that what Damien has imaged is the result of a volcanic eruption on Io. So that's pretty impressive. We're talking about detecting volcanoes on Venus. This is detecting volcanoes on Io. And bear in mind that this was 1.27 arc seconds in diameter when they took this image. So pretty amazing resolution. Yeah, this is John's compilation of the image and where it is. So this area of Akala Fluctus here is a kind of brighter area on Io, and it seems to line up with where Damien's bright spot was. So if that turns out to be a new feature, that will be pretty amazing, I think, for an amateur observer to have discovered something that on a moon of Jupiter. Talking of other small planets, Uranus has been around, but again is disappearing. This one from Luigi Moroni shows possibly some sort of albedo features in the clouds of Uranus, but not the most exciting of worlds. So, I'll move on to my specialist subject, which is the comet that's around at the moment. And you may well have seen in the media, and I've had lots of people say to me, have you seen the green comet streaking across the sky yet? Well, yes, I have seen a very faint fuzz in my binoculars. And if streaking across the sky means it moves about the diameter of the moon in 5 hours, then that really is streaking across the sky. But here we are, it is a comet. It's grandly known as 2022 E3 ZTF because comets are all discovered by survey telescopes now, so they don't get named after people, which is a real shame. ZTF is the Zwicky Transient Facility. Zwicky was an interesting character, but that's a different story. But they're looking for transients, so all sorts of things that move or outburst in the sky. They discovered this comet. And for us, it's extremely well placed. So it's just gone past perihelion, its closest point to the sun. It's approaching the Earth, and it will be at its closest to the Earth at the end of January, so February the 1st. And because of its orbit, it's actually going very high in the sky for us. Most of the time, comets we see are low in the sky, difficult to get. This one is high up. So it actually passes, it's down here at the moment, just here. It's going to pass very close to Polaris, so this is Ursa Minor. This is the plough here. It's pretty easy to find. I mean, I've found it in binoculars from my back garden in Chelmsford. It's pretty well defined. It's quite a nice, reasonably bright fuzzball. And it's been a very odd comet in that it's been incredibly well behaved. Most of the time with comets, we never really quite know what they're going to do. This one has been very, very well behaved. Its orbit, the reason that we get such a good view of it is its orbit is essentially starting up in the high north. It's diving down. We're just about to cross its orbit plane in the next couple of days, so we will see what effect that has. But it's been north of the ecliptic, which means it gives us a very, very good view. Paul did a visual observation of it. Was this yesterday? 2 days ago. When he estimated it to be about magnitude 6.2. It's probably somewhere around 5.8, 5.9 now. Now that's, in cometary terms, a comet that's 5.8 or 5.9 is not like a star that you could see fairly easily. It's quite diffuse. And so this may be naked eye, possibly naked eye from a dark site, but it's certainly a relatively easy binocular object. The light curve, as you can see, is incredibly well behaved all the way from when it was, discovered to now. It's behaving pretty much as we expected, and we expect it will probably reach about 5th magnitude at the end of this month. So you've got a couple of weeks to see it now. The moon will start becoming a nuisance in the evening sky in a few days or so. It will then, but it's still best in the morning sky. So one of the reasons I'm looking a bit more haggard than normal is that I've been up at 3 o'clock in the morning every morning for the last 5 days to take images of this comet. So it's certainly not like this one. This is the one that we saw 2 years ago. This is Neowise 2020 F3. But it illustrates quite nicely the two different tails that comets have. So you have a dust tail, which is essentially a whitish yellow tail because it shines by reflecting sunlight. And you have an ion tail, which is a bluish tail because it's shining by emission, mainly from carbon monoxide ions. So gas goes into the coma, gets blown back by the solar wind. And this gas then fluoresces, and it gives you that nice blue color. But just a warning, if you're going to try and take some pictures of this comet, and you're in a slightly light polluted place, you might be tempted to use a light pollution rejection filter. And one of the most popular light pollution rejection filters effectively completely would suppress that 425 nanometer blue light from the ion tail. So if you are going to take pictures of this comet, don't use a light pollution rejection filter, or if you do use one, check to see what its cutoff is, because otherwise you won't see the ion tail at all. It's been growing rapidly. This is an image by David Swan from about 12, 13 days ago, when it was dominated by dust, but you can see that small ion tail just coming out at the top. This is a nice picture from Denis Brzezinski up in Tarbet Ness using a Takahashi astrograph. And you've got the colors here. So you've got the ion tail, you've got the green coma, and you've got the yellowish, whitish dust here. Now, the ion tail has been the kind of big thing that everybody's been talking about with this comet because it's been growing and growing. And it changes from not just night to night, but from hour to hour and even minute to minute. So this is a picture I took of it on the 17th, and it shows a rather nice bit of structure and a split in the tail. This is Mazen Younes's picture that he took from his remote telescope in Morocco, showing the same thing. You've got the green coma there and a very impressive straight ion tail. This was taken by Peter Carson from Pagelsham on the Essex coast with a 100mm f2 lens. So you can actually get quite impressive images of this comet, even using just a DSLR and a camera lens. If you can find a reasonably dark site, you can trace the ion tail pretty much out of the frame here, and right around the centre here you've got the dust from the comet, which we're seeing almost in profile now behind the comet. So this is why this is widening up to quite a big fan. Anyone who's been up to see the comet over the last few days will realise it's been blooming cold in the morning. And Peter says that he was out at Pagelsham in his car and everything froze up and he couldn't actually open the doors, the tailgate of his car to get back in. Luckily he could get the driver door open and he had to put all of his equipment back into the car through the driver's door. So you might think that that's a bit of a problem, you know, cold weather. But it's nothing compared to this. This is where Dan Bartlett takes his comet images from. It's Dune Lake in California, high in the mountains. They've had a lot of snow there. Dan uses a Celestron 11, Rasa, Roa, Ackerman, Schmidt, and had to dig a big hole to get this working. So that's pretty good dedication for you, I think. And I think, Peter, your moan about the tailgate in your car freezing up is nothing.
And a long walk home, though.
It would have been a long walk home, but at least you haven't got 6 foot of snow to walk through. But Dan's pictures are just stunning. He has a really dark sky. He's up in the mountains, so he just gets absolutely amazing pictures of the comet. Other people have been submitting pictures. This is Peter Tickner, who does a lot of planetary stuff, has also been imaging the comet, which is great. And Mark Charon here took this image a few days ago using a Samyang 135mm f2 lens, which is a really good lens, actually. It's a very kind of economical, fast, medium focus lens. And that shows the dust fan and the ion tail really nicely. But the ion tail is a very fickle thing because it depends on what the solar wind is doing. And because the sun's been so active recently, what happened a few days ago was what's called a disconnection event. So essentially what happens here is that the ion tail, which is driven by the solar wind and the interplanetary magnetic field, because of something the sun did a little while before, the magnetic field reverses at the comet and it effectively rips the ion tail off the comet. So this is what was the ion tail, and you can see it moving back here over a period of about an hour, and the comet's generating a new highly collimated tail before it. So essentially, if people take long exposures of the comet, all of this gets smeared out. So one of the things about taking pictures of comets, if you want to pick up detail in the ion tail, is you need to keep the exposure short because of this activity. But essentially what's happened to the comet now is that the ion tail has been completely disrupted by this disconnection event. And this is what it looked like this morning. So you've got this huge area of dust, which is the dust tail, and the ion tail has kind of disappeared into a chaotic little fan here. You also have dust coming out the front as well, because we're just about to cross the orbit plane of the comet. So it looks very, very different now. But other people were out this morning too. Just got a couple more pictures to show you of the comet before we finish. This was posted to the BAA website during this meeting by Hugh Allen. It's a spectrum of the comet that he took this morning. And most of what we can see when we look at a comet is what's called the swan band emission, which is this carbon emission, which is greenish in colour. But there's a huge emission from cyanogen, which is in the violet. Too short a wavelength really for us to see, but the comet is really active in that. So really good to see spectra again of this comet. and the ability of amateurs to take spectrograms of comets has improved a lot over the last few years. And this isn't a particularly bright comet, but getting really good quality spectra is great. And then this, which I think is an absolutely fantastic image, by David Strange, taken this morning using one of these little Red Cat 51s, which is a sort of photographic telescope. It shows a lot of features here. So you've got the green coma, you've got this huge dust fan, which if you imagine what this is the tail of the comet, the dust tail of the comet projected back into the screen. So we're looking almost along its orbital plane. And then you have this little vestigial ion tail here. So who knows what's going to happen to this comet over the next couple of weeks? We can predict accurately where it's going to be. We can predict probably pretty accurately how bright it's going to be. We really don't know how the tails are going to develop and what it's going to look like. So do take the opportunity to get out and have a look at it, because even though it's not a bright green comet streaking across the sky, it's a pretty nice comet. It's kind of binocular object. Naked eye, possibly in a really dark site. At the moment, it's best seen in the morning sky, and it probably will remain best seen in the morning sky simply because the moon is coming into the evening sky now. But you don't need to be getting up at 3 a.m. to see it. You can actually see it sort of midnight. It's beginning to rise, and as it gets closer to the pole, it'll be easier and easier to observe all the way through the night. Just a couple more comet ones, and then we'll be on to the final leg of this. So this is comet 10 minutes.
More than 10 minutes.
It'll be 5. 29. This is 29P Schwarzmann-Bachmann, which is a comet which is very different to ZTF. It's a comet which is in an orbit similar to Jupiter's orbit. It's a big comet with a nucleus maybe 60 kilometers across. It keeps going into outburst. And Richard Miles runs a program for the comet section looking at it, and we've had a very large number of outbursts recently of this comet. So lots and lots of interesting stuff to do in the comet world. So in my last 5 minutes or so, just variable stars. There's a few variable stars that are worth you looking at. This one, GK Persei, was a nova that went off in 1901. It got to magnitude 0.2 when it was a nova, but it now seems to have turned in from a normal nova into a recurrent nova. And you can see every now and again it brightens up, and the most recent brightening has just happened. And Mike Harlow taken an image of it there between the bars, and he's also used his objective prism, which is just a glass prism in front of the telescope, to take a spectrum of it. So you can see here, unlike the spectra that people do with the spectrograms that produce things like Hugh Allen's spectra, this actually produces an image of the spectrum of every object in the field. And you can see here GK per, and you can see various lines in it. So this objective prism approach used to be something the professionals used a lot. They don't now, but it's a really interesting approach for amateurs to use. And this is actually an objective prism, which I think was part of the BAA instrument collection originally. Another one that's worth looking at is this. It's what's called a blazar. It's actually a galaxy, an active galactic nucleus, which has gone into outburst. And it's the brightest it's ever been. It's about 12th magnitude. And it's an extremely long way away, because essentially what we're seeing is the collimated light from one of these quasars. So that one's worth finding. It's in Pisces, so it's kind of reasonably accessible. And then the final one, I mentioned it last time at Christmas, RW Cephei, which is a sort of similar thing to Betelgeuse, in that this star fluctuates about a bit, but it's gone into quite a big fade now. And it's a naked eye, it's a binocular object. It's something that you can actually estimate quite well with binoculars. Definitely worth, if you're out with binoculars, having a look and seeing if you can make a magnitude estimate of this one. And then finally, David, I just wanted to mention this. Lots of you will have seen this, hopefully, on the BBC website. A really, really good write-up about light pollution. I've had lots of people mention this to me in the last couple of days, and it's really good from the point of view of just people's recognition of the fact that light pollution is a real problem, not just to us, not just to astronomers worried about seeing things in the night sky, but to all sorts of things, to people's health, to the health of wildlife. There's a really good set of links on that BBC page that take you to various things. This I thought was really good. It's from the Royal Horticultural Society, and it was on a page about lighting up your gardens. So, you know, people seem to like their lighting up trees and lighting up their gardens so it looks pretty, but it has a horrible effect on wildlife, insects in particular.
And the security lights as well.
Security lights are just the worst.
Absolutely.
Worst of the worst.
Spoils my observing.
Yeah, it does for a lot of people, and security lights, they're not really security lights because, I mean, I've got a neighbour who's got one that comes on if a fly flies past and it stays on for 5 minutes. You know, it's that silly. And another thing, I was looking at, I don't normally read the comments on the BBC website, but I thought I'd read this one. And 95% of the comments were all about, yeah, this is terrible, it's a terrible waste of energy, it's a terrible impact on our environment. There was one that particularly caught my eye, though, because it's very characteristic of what's happening around where I live, and it's this one. It says, it isn't helped by the growing trend for people to floodlight their suburban homes, drives, doorways, gate posts, cars and gardens as if they're some kind of national monument. It's utterly bizarre, naff and unnecessary. And it is. I have houses around me that are just kind of normal houses where they've actually lit up the front of the house as if it's a church or a castle or something. I just cannot understand it.
Have you challenged them there? That friendly way that you
knock on the door. Why are you doing this naff thing? Anyhow, it's a really good article, and I think it does show that there is a lot of public traction for this. If only we can actually just get people to sort of take that seriously, because it affects so many things. Anyway, thank you everybody. David, hopefully that was done in time, and hope you enjoyed the meeting.
Yeah.
It's great to see some positive publicity from BAA limiting light pollution. Right, well, all good things must come to an end, and we have to be out of here. The IOP staff have been very generous to us. Thanks very much to Simon for his work on the technical side. Thanks also to Andy Wilson, who's gone now, for his work helping us to stream the meeting. And we'll be back here in March, as I said earlier, but we must now all get out and see you all another time.
Yeah, me too.